Step outside tonight. Find somewhere dark, somewhere quiet, and look up. You know this sky. The moon, the scatter of stars, the familiar emptiness between them. You've seen it 1,000 times. Now imagine something else is there. Stretching from one horizon to the other, a massive arc of light cuts across the darkness. It doesn't move, it doesn't rise or set like the moon. It's simply there, an enormous, luminous band carving the sky in half, brighter than anything you've ever seen overhead. And it has been there since the night you were born. Since the night your great-great-grandparents were born. Since before there were people at all. Earth has rings. Not thin, wispy things like Jupiter's, those faint halos of dust you'd need a spacecraft to photograph. These are rings you can see with your bare eyes from any rooftop, any ocean, any desert on the planet. Dense bands of rock and debris orbiting above the equator, catching the sunlight and scattering it back down like a second permanent sky. And they change everything. They change the way the night looks. Under rings like these, the sky never truly goes dark. Sunlight bounces off billions of orbiting particles, pouring a soft silver glow across the landscape long after sunset. The Milky Way, that river of distant starlight humans have gazed at for hundreds of thousands of years, becomes invisible, washed out, gone. They change the climate. Rings cast shadows, and those shadows shift with the seasons as Earth tilts on its axis. In summer, the shadow falls on the opposite hemisphere, making its winter colder. During the equinoxes, the shadow slides directly over the tropics, blocking sunlight from the warmest latitudes on the planet. Temperatures drop, growing seasons shrink. Entire ecosystems reshape themselves around the geometry of a shadow that stretches thousands of kilometers wide. They change civilization. Every ancient culture that built temples toward the stars, every sailor who navigated by constellations, every philosopher who looked up and asked, why? All of them would have grown up beneath an arch of light that dominated the sky more than any star, any planet, any aurora ever could. The rings wouldn't just decorate their mythology, the rings would be their mythology. And they change our ability to leave. Rockets launched from the equator would have to punch through a field of orbiting debris moving at nearly 8 kilometers per second. A pebble the size of a marble at that speed carries the energy of a hand grenade. The rings wouldn't just be beautiful, they'd be a barrier, a natural minefield between us and the rest of the universe. This is not entirely science fiction. Saturn's rings are real, spectacular, yes, wide enough to stretch almost from Earth to the moon, yet thin enough that if you shrank them down to the size of a football pitch, their thickness would be less than a razor blade. Billions of ice particles, some as small as grains of sand, others as large as houses, all orbiting in an impossibly flat disk around the planet. And Saturn is not alone. Jupiter has rings, Uranus has rings, Neptune has rings. Every giant planet in our solar system wears them, so why not Earth? The answer may surprise you, because Earth might have already had them. In 2024, a team of geologists at Monash University in Australia published a study that sent a quiet shockwave through planetary science. They had mapped 21 ancient impact craters, all dating to roughly the same geological period, around 466 million years ago, and discovered something that shouldn't happen by chance. Every single one of those craters sat within 30 degrees of the equator. The probability of that occurring randomly, given that more than 70% of Earth's continental crust lies outside that narrow band, is roughly 1 in 25 million. Their hypothesis, a large asteroid, perhaps 12.5 kilometers across, wandered too close to Earth and crossed a boundary known as the Roche limit, the distance at which a planet's gravitational pull tears an incoming object apart. The asteroid didn't slam into the surface. It shattered in orbit. And for the next 20 to 40 million years, Earth wore a ring of rocky debris around its equator. That ring may have cast enough shadow to trigger one of the coldest periods in the last 500 million years. Temperatures plummeted by as much as 8 degrees Celsius, ice sheets advanced, and the late Ordovician mass extinction followed, an event that wiped out roughly 85% of all marine species on the planet. A ring of debris in the sky, and an extinction event on the ground. Tonight, we're going to explore what it would mean for Earth to have permanent rings. Not a temporary debris field that fades over geological time, but a lasting, visible, structural feature of our planet, as constant as the moon, as ancient as the oceans. We'll begin with Saturn because to understand what Earth's rings could be, we first need to understand what rings are, how they form, how they behave, why they exist at all. Then we'll bring that knowledge home. We'll stand at different latitudes and look up. We'll watch the shadows fall and the seasons warp. We'll trace the ring's fingerprints on mythology, navigation, science, warfare, art, and on the fundamental question of whether a ringed Earth could ever have launched a single satellite into orbit. And we'll return to that ancient ring, the one Earth may have actually worn 466 million years ago, and ask what it left behind. If you enjoy this kind of exploration, where science meets wonder and the familiar becomes extraordinary, consider subscribing to the channel. And let me know in the comments where you're listening from tonight. It's always something special to see just how far across the world these conversations reach. To understand what Earth's rings might look like, we first need to understand what rings actually are. And for that, we need to visit the most spectacular ring system in our solar system, a structure so vast it could nearly bridge the distance between Earth and the Moon, yet so thin that if you turned it sideways, it would vanish. Saturn is waiting. In the summer of 1610, Galileo Galilei pointed a homemade telescope at Saturn and saw something he couldn't explain. The planet appeared to have ears. Two bright lumps clung to either side of its disk, perfectly symmetrical, perfectly still. He sketched them carefully, wrote letters about them, and spent months trying to figure out what he was looking at. 2 years later, they vanished. He checked his telescope. He checked his notes. He looked again. The lumps were gone. Saturn appeared perfectly round, naked, as though nothing had ever been there at all. Galileo was baffled. He reportedly asked whether Saturn had devoured its own children, borrowing from the old myth of the god Kronos swallowing his sons. He never solved it. What Galileo couldn't know, what no one would understand for another half-century, was that Saturn's rings had simply turned edge-on to Earth. That razor-thin disk, when viewed from the side, disappears. It would take until 1659, when the Dutch astronomer Christian Huygens peered through a far better telescope, to recognize that Saturn was surrounded by a thin, flat ring, nowhere touching, inclined to the ecliptic. 16 years later, Giovanni Cassini discovered a dark gap splitting the ring into two, the division that still carries his name. What none of them could have imagined was the scale of what they were looking at. Saturn's rings span roughly 280,000 kilometers from edge to edge. That's close to 3/4 of the distance between Earth and the Moon. If you could peel them off Saturn and lay them flat across the inner solar system, they'd stretch from here to the Moon and most of the way back. They are, by any measure, one of the largest visible structures in our solar system. And yet they are almost impossibly thin. The main rings average about 10 meters in thickness. Some sections may be as thin as 5. To grasp what that means, imagine shrinking the entire ring system down to the size of a football pitch, 100 meters across. At that scale, the rings would be thinner than a sheet of paper, thinner than a human hair. You could run your finger across the model and never feel them. This is one of the strangest facts in planetary science. A structure wide enough to nearly reach the Moon, yet so flat you could slip it under a door. What makes that possible is what the rings are made of. They are not solid. They're not a disk of metal or stone. Saturn's rings are a swarm, billions upon billions of individual particles, each one in its own orbit around the planet, each one held in place by the balance between Saturn's gravity, pulling inward, and its own orbital velocity pushing outward. The particles range from grains of sand to chunks the size of a car, with a few rare boulders as large as a small house, and almost all of them, more than 95% by mass, are water ice, clean, bright, reflective water ice. That's why Saturn's rings shine the way they do. Sunlight hits those countless ice particles and bounces back. From Earth, even through a modest backyard telescope, the rings gleam. They catch the light with a brilliance that no other planetary feature can match, because ice is an extraordinary reflector. Freshly exposed water ice can bounce back more than 90% of the sunlight that strikes it. The rings are organized into distinct bands, each with a letter designation that reflects the order of their discovery rather than their position. The broadest and brightest is the B ring, a dense wall of icy particles that contains roughly 2/3 of the total ring mass. Just outside it lies the A ring, separated by that dark gap Cassini spotted in 1675. Closer to the planet sits the C ring, fainter, thinner, sometimes called the crepe ring for its translucent appearance. And beyond these three main bands, fainter rings extend both inward and outward, some so tenuous they were only discovered by spacecraft flying through the system. The total mass of all these particles, everything orbiting Saturn in that thin plane, is roughly equivalent to a single icy moon about 400 kilometers across. That's smaller than Saturn's moon Mimas. All that grandeur, all that visual spectacle, compressed into a mass you could fit inside a modest asteroid. For centuries, scientists assumed the rings were ancient, that they had formed alongside Saturn itself 4.5 billion years ago and had been orbiting ever since. It was a natural assumption. Saturn without its rings seemed as unthinkable as Earth without its moon. The rings looked permanent, eternal, part of the planet's identity. Then Cassini arrived. NASA's Cassini spacecraft entered Saturn orbit in 2004 and spent 13 years studying the planet, its moons, and its rings in extraordinary detail. And what it found overturned everything. During its final orbits in 2017, Cassini dove between the rings and the planet itself, threading a gap no spacecraft had ever entered, and measured the gravitational pull of the ring material directly for the first time. The rings were light, far lighter than expected, and that lightness carried a devastating implication. They couldn't be old. If the rings had been orbiting for billions of years, they would have accumulated a dark coating of interplanetary dust, the slow, steady rain of micrometeorites that dulls every surface in the solar system over time. The rings were too bright, too clean, too pure. The ice was too fresh. The conclusion, published in the years following Cassini's final plunge into Saturn's atmosphere, was startling. Saturn's rings are young, perhaps only 100 to 200 million years old, younger than the dinosaurs, younger than most of the fossils in your local natural history museum. Something created them relatively recently in solar system history, and whatever that something was, it was violent. The leading theory, proposed in 2022 by a team at MIT, suggests that Saturn once had an additional large moon. The researchers nicknamed it Chrysalis. Around 150 million years ago, gravitational interactions with Saturn's other moons destabilized Chrysalis's orbit and sent it spiraling inward, past the Roche limit, into the zone where tidal forces overwhelm a body's own gravity and tear it apart. Chrysalis shattered. Most of its mass fell into Saturn. A fraction remained in orbit and became the rings. There is a quiet tragedy in this. The rings are not just young, they are dying. Cassini also measured what scientists call ring rain, a steady drizzle of ring particles spiraling into Saturn's atmosphere along magnetic field lines. The rate is staggering. Roughly 10,000 kilograms of material every second pouring off the inner edge of the rings and falling into the planet's cloud tops. At that pace, Saturn's rings have perhaps another 100 million years before they fade entirely. A blink in geological time. The most beautiful structure in the solar system is temporary. It appeared after the dinosaurs, and it will be gone before the sun begins to die. We happen to exist during the brief window in which Saturn wears its rings. 100 million years earlier, and we would have seen a bare planet. 100 million years later, the same. The rings are not a permanent feature of the solar system. They are an event, a spectacle with a beginning and an end, and we are lucky enough to be alive for the middle act. Saturn's rings exist because of a specific set of conditions. A massive planet with an enormous gravitational field, a source of material, whether a shattered moon or a captured comet, and a location far enough from the sun that water ice can survive indefinitely in open space. Those conditions produce the brightest, most photogenic ring system imaginable. Take away any one of them and the rings change. Move the planet closer to the sun, for instance, and ice becomes a problem. Water ice sublimates. It transitions directly from solid to gas when exposed to intense solar radiation. At Earth's distance from the sun, a ring of pure ice would not last. The particles would slowly evaporate, thinning the ring over millions of years until nothing remained but a faint haze of vapor. A ring around Earth would have to be made of something else, something tougher, something that can withstand the heat. Rock. Saturn's rings exist in the frozen outer reaches of the solar system, nearly 1.5 billion kilometers from the sun. They are ice because they can be. Closer to our star, on a small rocky world with oceans and an atmosphere, a ring system would look different, behave differently, and form through entirely different means. The question is, how does a planet like Earth get rings in the first place? Every ring system in the solar system exists for the same reason. Something came too close to a planet and was torn apart. The physics behind this is elegant and brutal. In 1848, a French astronomer named Édouard Roche sat down and calculated the minimum distance at which a celestial body could approach a larger one without being ripped to pieces by tidal forces. The answer depended on the densities of both objects, the planet and the intruder, and the result defined an invisible boundary around every planet in the solar system. Cross that line, and you don't survive. Your own gravity, the force holding you together, becomes weaker than the difference in gravitational pull between your near side and your far side. The planet stretches you, cracks you, and eventually reduces you to a cloud of fragments, each one settling into its own orbit. That boundary is called the Roche limit, and it is, in the simplest terms, where rings are born. For Earth, the Roche limit sits at roughly 18,400 kilometers from the planet's center for a fluid or loosely bound body. A rubble pile asteroid, for instance, held together more by friction than by solid rock. For a rigid, dense object like a solid iron meteorite, the limit shrinks to about 9,500 kilometers. Anything between those two numbers is the danger zone, the region where an incoming body's fate depends on what it's made of and how tightly it holds itself together. Our moon orbits far beyond this boundary at 384,000 kilometers, more than 20 times the Roche limit. It's safe, it has always been safe, and it's actually moving farther away, receding from Earth at about 3.8 centimeters per year as tidal interactions slowly transfer rotational energy from the planet to the moon's orbit. No force in the current solar system is pushing the moon back inward. The moon will not become a ring. That doesn't mean Earth has never had one. The most dramatic ring-forming event in Earth's history happened before there was an Earth to speak of. 4.5 billion years ago, when the solar system was still young and its inner reaches were a shooting gallery of half-formed worlds, a body roughly the size of Mars, a protoplanet scientists have named Theia, collided with the young Earth. The impact was not a glancing blow. Simulations suggest it was a violent, nearly head-on collision that liquefied much of both worlds, blasting an enormous volume of molten rock and vaporized material into orbit. For a brief period, perhaps only hours, perhaps days, Earth wore a ring. a thick, seething disk of superheated debris encircling the planet, glowing orange and red against the blackness of space. NASA simulations published in 2022 suggest this disk formed almost immediately after impact, within the first few hours, and it was massive, carrying roughly 20% of Earth's eventual mass in suspended debris. It didn't last. Within a few thousand years, possibly less, gravitational interactions within that disk caused the material to clump together. Collisions built larger and larger bodies from the wreckage, and eventually, over perhaps a few million years, most of that orbiting debris coalesced into a single object. The Moon. Your moon, the one you see rising over the rooftops, the one that pulls the tides and steadies the planet's axial tilt, was once a ring around Earth. A temporary, violent, incandescent ring that existed for a geological instant before gravity gathered it into a sphere and sent it on a slow outward spiral that continues to this day. Thayer's ring was never going to be permanent. It was too massive, too hot, and too far outside the Roche limit for most of its material to remain dispersed. Gravity won, as gravity always does when you give it enough mass and enough time. The ring became a moon, and that moon became the single most important stabilizing force in Earth's geological and biological history. So that's one way to get a ring, a catastrophic planetary collision. Spectacular, yes. Repeatable, no. At least not in any way that leaves a planet habitable afterward. Thayer-scale impacts are features of the early solar system, not the mature one. The inner planets cleared their orbital neighborhoods billions of years ago. Nothing that large is coming our way again. A second path to rings is gentler, though only by comparison. Asteroids wander. Their orbits are not fixed lines etched in space, but slow curves shaped by the gravitational nudges of Jupiter, Mars, and even Earth itself. Over millions of years, those nudges shift an asteroid's path, sometimes outward into safer orbits, and sometimes inward toward the Sun or toward a close encounter with a planet. Most asteroids that approach Earth either miss entirely, burn up in the atmosphere, or slam into the surface. The craters they leave behind are scattered across every continent. A rare few, though, approach at just the right angle and just the right speed to be captured, temporarily trapped by the planet's gravity before either escaping again or spiraling inward. And if one of those captured bodies happens to cross the Roche limit, it doesn't need to hit the surface to leave its mark. Tidal forces do the work. The asteroid, particularly if it's a rubble pile, a loose aggregate of rock, dust and ice held together by weak self-gravity, begins to stretch, crack and fragment. The pieces spread along the orbital path. Over time, collisions between fragments grind the material finer and distribute it more evenly. A ring forms. This isn't speculation, it's a prediction for another world in our own solar system. Mars's moon Phobos, a small, irregularly shaped body just 22 kilometers across, is spiraling inward. Unlike Earth's moon, which moves away from its planet, Phobos is falling toward Mars at a rate of about 1.8 centimeters per year. In roughly 50 million years, it will cross the Martian Roche limit. And when it does, Phobos will not crash into the surface. It will break apart slowly at first and then catastrophically, spreading into a thin ring of debris around the red planet. Mars will get rings. It's not a question of if, it's a question of when. There is a third scenario, one that lives more in the realm of thought experiment than realistic projection, yet is worth considering for what it reveals about orbital mechanics. What if the moon itself somehow reversed its slow, outward drift and began falling back toward Earth? It won't happen. There is no known mechanism that could reverse the tidal transfer of angular momentum currently pushing the moon away. No rogue planet is going to knock it inward. No passing star will perturb its orbit enough to send it spiraling home. The moon is safe, and this scenario exists purely in the imagination. Still, the physics is clear. If the moon were somehow brought within the Roche limit, closer than about 9,500 kilometers for a rigid body of its density, tidal forces would begin to deform it. The near side, pulled harder than the far side, would stretch outward. Fractures would propagate, chunks of lunar crust would break free, and over time, the entire body would disintegrate into a vast ring of rock, dust, and regolith orbiting the Earth. It would be the most visually dramatic ring in the solar system, a ring made not of anonymous asteroid fragments, but of the Moon itself, a body humans have watched, worshipped, and navigated by for hundreds of thousands of years, reduced to a glittering band across the sky. None of these scenarios, though, produce a ring of ice. That's the critical distinction between a ring around Saturn and a ring around Earth. Saturn sits 1.4 billion kilometers from the Sun. At that distance, solar radiation is weak enough that water ice can persist indefinitely in open space. Particles can orbit for hundreds of millions of years without significant sublimation. The ice stays frozen, the ring stays bright. Earth orbits at 150 million kilometers, nearly 10 times closer. Here, solar radiation is fierce. A chunk of exposed ice in Earth orbit would begin losing mass almost immediately, sublimating from solid to gas as the Sun's energy breaks molecular bonds on its surface. A ring of pure ice around Earth would thin, fade, and eventually vanish. Not in billions of years, not even in millions, depending on particle size, possibly in thousands. An enduring ring around Earth would have to be rock, silicate, metal, dust, darker than Saturn's gleaming ice, less reflective, grittier, yet still visible, still substantial, still capable of catching sunlight and scattering it back to the surface. Think less of a polished mirror and more of a band of pale stone, luminous against the black of space but never quite as dazzling as what Cassini photographed around Saturn. So the ingredients are these: a rocky planet with a well-defined Roche limit, a source of material, whether from a shattered asteroid, a catastrophic collision, or the slow tidal destruction of a moon, and a location close enough to the Sun that only rock and metal survive. The result is a permanent ring of stone and debris, orbiting above the equator, casting light downward at night and shadows during the day. The question that follows is the one that matters most to anyone standing on the ground, looking up. If Earth had those rings, a permanent, visible, structural feature of the sky, what would they actually look like? The first thing you need to understand about Earth's rings is that they would never move. Not the way the moon drifts across the sky each night, not the way the stars wheel overhead as the planet turns. The rings would be fixed, locked in place above the equator, tracing the same arc across the same patch of sky, hour after hour, season after season, century after century. You could step outside at midnight and find them exactly where they were at noon. You could return 1,000 years later and nothing would have changed. This is because the rings orbit in Earth's equatorial plane. Each particle follows its own circular path around the planet's midsection, and from the ground that collective orbit projects as a single luminous band arcing from horizon to horizon. The Earth rotates beneath the rings, but the rings themselves, as seen from any fixed point on the surface, stay put. They are as permanent a fixture of the sky as the ground beneath your feet. What changes is how they look, and that depends entirely on where you're standing. Imagine yourself at the equator: Quito, Ecuador, Jakarta, Indonesia, Nairobi, Kenya. From any of these cities, you would see the rings edge on, the entire vast disk, thousands of kilometers wide, compressed into a single luminous line rising straight up from the horizon, climbing through the zenith directly overhead and descending to the opposite horizon. A thread of light bisecting the sky from east to west. Thin, bright, and impossibly straight, like someone had drawn a ruler across the heavens and traced it with silver. You might not even recognize it as a ring at first. From the equator, the structure has no width. It's a line, not a band, and depending on the ring's actual thickness and density, it might appear no wider than a contrail left by a passing aircraft. Brilliant, yes. Permanent, yes. But nothing like the sweeping arch visible from higher latitudes. Now move north, fly to Guatemala City, roughly 14 degrees above the equator. Step outside and look south. The line has thickened. It's no longer a razor edge cutting the sky in half. It's beginning to open up, spreading into a visible band that stretches across the southern horizon with a perceptible width. You can start to see it as a structure, something with dimension, something occupying real space rather than a geometric abstraction drawn on the dome of the sky. Keep moving. Fly to Istanbul, 41 degrees north. And here the rings transform into something else entirely. From the mid-latitudes you see them at an angle, a great sweeping arch spanning the southern sky, rising from the southwest horizon, climbing to its highest point due south, and descending again to the southeast. The arch is wide, luminous, structurally dominant in a way no natural sky feature on our Earth can match. It doesn't look like a cloud or an aurora. It looks permanent, solid, architectural, as though someone had built a bridge across the sky and forgotten to take it down. Washington, D.C., London, Tokyo, Buenos Aires. From any city in the mid-latitudes, the rings would command the sky. They would be the first thing you noticed when you walked outside, the last thing you saw before you closed your eyes at night, and the single most prominent visual feature of the natural world. Travel farther still, to Tromsø, Norway, or Fairbanks, Alaska, near the Arctic Circle, and the rings sink toward the horizon. From extreme northern or southern latitudes, the arch flattens into a low, glowing hump, barely rising above the rooftops, visible but diminished, a distant reminder of the spectacle that dominates the skies closer to the equator. No two places on Earth would see the same sky. A child growing up in Quito would know the rings as a vertical line. A child in Istanbul would know them as a great arch. A child in Reykjavik would barely see them at all. The rings would create a visual geography of the sky, a new way of understanding where you are on the planet based not on landmarks or maps, but on the shape of the light overhead. And then there is the question of brightness. Saturn's rings shine because they're made of ice, and ice is among the most reflective natural materials in the solar system. Earth's rings, as we've established, would be rock, darker, rougher, less mirror-like. A rocky ring would not blaze with the same intensity as Saturn's. It would glow rather than gleam, reflecting perhaps 30 to 40% of incoming sunlight compared to ice's 90%. That is still extraordinarily bright. 30% reflectivity spread across a band thousands of kilometers wide and composed of billions of individual particles would produce a structure easily visible in broad daylight. During the day, the rings would appear as a pale, luminous stripe against the blue, fainter than the sun, brighter than any cloud, always present, always in the same position. At dusk and dawn, as the sun dipped below the horizon while the rings still caught direct sunlight high above, the band would intensify, glowing against the darkening sky with a cool, silver-white radiance. And at night, the rings would transform the world. Sunlight reflecting off the ring particles would pour down onto the night side of the planet, a phenomenon scientists call ring shine. The effect would be dramatic. On a clear night with no moon, the rings alone could illuminate the landscape with a soft, diffuse glow brighter than a full moon. Shadows would appear beneath trees. Roads would be visible without streetlights. The darkness that humans have known for their entire evolutionary history, that deep velvet black that allowed our ancestors to see the Milky Way in all its detail, would simply not exist. The sky would never be fully dark, not anywhere on the planet, not at any time of year. The rings would see to that. The appearance of the rings would also shift with the seasons, though the rings themselves would not move. Earth's axial tilt, that 23.4-degree lean that gives us summer and winter, means that the sun's position relative to the ring plane changes throughout the year. During the solstices, sunlight strikes the rings at their maximum angle, illuminating one face brightly while leaving the other in partial shadow. The ring appears asymmetric, one half brilliant, the other dim, During the equinoxes, the sun aligns almost perfectly with the ring plane. Sunlight streams through the ring edge-on, and for a few days each March and September, the rings catch the light at their most dramatic angle. A blinding strip of reflected sunlight that seems to intensify just as the days and nights reach equal length. Ancient cultures would have noticed this. They would have built calendars around it. The equinox brightening of the rings would have been one of the most reliable astronomical events on a ringed Earth. As predictable as sunrise, as visually striking as a solar eclipse, and happening twice every year without fail. One more effect deserves mention. At midnight, when your location on Earth faces directly away from the sun, the planet itself casts a shadow on the rings. You would see it clearly, a dark bite taken out of the ring's bright band, a curved absence of light directly opposite the sun's position. Earth's own shadow projected onto its own rings, a nightly reminder that the light you're seeing isn't generated by the rings themselves, but borrowed from a star 93 million miles away. The rings would be beautiful. That much is beyond question. From every latitude, in every season, under every lighting condition, they would dominate the human experience of the sky. They would be the most prominent natural feature visible from the surface of the planet, more constant than the moon, more visible than the stars, more structurally imposing than any mountain range or ocean. Their beauty, though, would come at a cost, because those billions of orbiting particles would not only reflect light downward, they would also block it, and the shadow they cast on the planet below would change the climate, the seasons, and the meaning of a clear day in ways that no civilization could ignore. A ring around Earth would not simply hang in the sky and look beautiful. It would stand between the planet and the sun, and anything that stands between a planet and its star casts a shadow. The geometry is straightforward. Earth's axis is tilted 23.4 degrees relative to its orbital plane. That tilt is what gives us seasons. The northern hemisphere leans toward the sun in June, away from it in December, and the cycle repeats. The rings, locked above the equator, don't tilt with the seasons. They stay fixed in the equatorial plane while the planet's relationship to the sun shifts around them. And that means the shadow the rings cast on the surface moves. In June, when the northern hemisphere tilts toward the sun, sunlight hits the ring plane from above, from the north in effect. The shadow falls southward, draping across the southern hemisphere during its winter months. The south's already shortened days become darker still. Less solar energy reaches the ground. Temperatures that would normally dip during winter drop further, and the cold lasts longer. 6 months later, the situation reverses. In December, with the southern hemisphere tilted sunward, the ring shadow migrates north. Northern Europe, Canada, Russia, Japan, regions that already endure long, cold winters, would lose additional sunlight to the dark band overhead. Snow that might have melted in March lingers into April. Rivers that typically thaw by spring stay frozen weeks longer. The growing season, that precious window between the last frost and the first, contracts. And then come the equinoxes. Twice a year, in March and September, the sun crosses the equatorial plane. For a few days around each equinox, sunlight streams directly along the ring plane, edge on, and the shadow falls where it is widest and most concentrated, straight down onto the tropics. The equatorial regions, the Amazon, Central Africa, Southeast Asia, Indonesia, some of the most biologically productive and agriculturally vital zones on the planet, experience a brief but significant dip in solar radiation. Not enough to freeze anything, not enough to cause immediate catastrophe. Enough, though, to matter. Enough to cool the air, suppress convective rainfall, and shift the behavior of weather patterns that billions of people depend on. The width and intensity of the shadow depend on the ring's optical depth, a measure of how much light the ring blocks versus how much it lets through. A thin, sparse ring would cast a faint shadow, more of a dimming than a darkness, and its climate effects would be modest. A dense, opaque ring like Saturn's B ring would throw a shadow sharp enough to visibly darken the ground beneath it, and the climate consequences would be severe. For a ring with moderate density, something between Jupiter's ghostly wisps and Saturn's brilliant bands, the effect on global temperature could range from 1 to 3 degrees Celsius of cooling. That might sound small. It is not. The difference between the current global average temperature and the peak of the last ice age is roughly 5 to 6 degrees. A ring-induced cooling of even 2 degrees would be enough to expand polar ice sheets, shift the boundaries of temperate agriculture, and push marginal ecosystems, coral reefs, alpine meadows, semi-arid grasslands, past their tolerance thresholds. And the cooling would not be uniform. That is what makes the ring shadow so disruptive. It doesn't reduce sunlight evenly across the globe the way a slight dimming of the sun itself would. It targets specific latitudes at specific times of year, creating bands of relative cold that migrate with the seasons. The southern hemisphere gets colder winters. The northern hemisphere gets colder winters. The tropics get hit during the equinoxes. The net result is a planet with more extreme seasonal contrasts, sharper temperature gradients between latitudes, and less thermal stability overall. Ocean currents, which are driven largely by temperature differences between equatorial and polar waters, would reorganize. The thermohaline circulation, that great global conveyor belt of warm and cold water that carries heat from the tropics to the poles and cold water back again, would respond to the altered gradients. Exactly how it would respond is difficult to predict because the system is non-linear and sensitive to small perturbations. What can be said with confidence is that it would respond. The currents that exist today are calibrated to a planet without rings. Change the thermal inputs and the calibration breaks. Rainfall patterns would shift as well. The tropics receive enormous amounts of rain because warm air rises there, cools as it gains altitude, and releases its moisture. Reduce the solar heating at the equator, even periodically, even by a fraction, and the engine that drives tropical rainfall weakens. Monsoons could arrive later, carry less water, or fail to materialize in years when the ring shadow is particularly dense. For the billions of people across South and Southeast Asia who depend on monsoon rains for agriculture, even a modest disruption could mean the difference between a harvest and a famine, and the effects would cascade. Less sunlight reaching the surface means less photosynthesis. Less photosynthesis means reduced plant growth, reduced oxygen output, reduced carbon dioxide absorption. Forests in the shadow zone would grow more slowly. Grasslands might recede. The base of the food chain, from phytoplankton in the oceans to cereal crops on land, would feel the pressure of a sky that gives a little less than it used to. None of this is pure speculation. There is a precedent, not from another planet, but from our own. NASA's Cassini spacecraft, during its 13 years orbiting Saturn, observed that Saturn's upper atmosphere behaves differently under the ring shadow. The ionosphere, the electrically charged upper layer of the atmosphere, is noticeably colder and denser in the regions where the rings block sunlight. Radio signals passing through those shadowed zones are disrupted in measurable ways. Saturn's own atmosphere reacts to the shadow of its own rings, and there is no reason to think Earth's atmosphere would do otherwise. And there is an even more direct precedent, one that brings us back to the geological record. If the hypothesis proposed by Tompkins and his colleagues at Monash University is correct, if Earth genuinely wore a ring of asteroid debris 466 million years ago, then we have already seen what ring shadows can do. The Hernantian Ice Age, which began during the late Ordovician, brought global temperatures down by as much as 8 degrees Celsius. Ice sheets expanded from the poles deep into what are now temperate latitudes. Sea levels plummeted as water locked up in glaciers. And the marine ecosystems that had flourished for tens of millions of years collapsed. Roughly 85% of all marine species went extinct. 8 degrees, from a ring that may have lasted only 20 to 40 million years. The shadow didn't need to be permanent to be devastating. It just needed to persist long enough for the climate to cross a threshold, and once crossed, the feedback loops took over. More ice meant more reflected sunlight, which meant more cooling, which meant more ice. The ring lit the fuse, and the planet's own physics did the rest. A permanent ring around Earth, one that endured not for tens of millions of years but for billions, would not necessarily produce the same catastrophe. Much depends on the ring's density, its width, and the composition of its particles. A thin, translucent ring might reduce global temperatures by a degree or less, producing effects that civilizations could adapt to. A dense, opaque ring could plunge the planet into a permanent state of enhanced glaciation, making the current ice ages look mild by comparison. The shadow of the rings would be the price of their beauty. Every glowing arch in the night sky, every silver band gleaming at sunset, would carry with it a cost measured in lost sunlight, lost warmth, and ecosystems pressed to their margins. The rings would giveth with one hand, light, wonder, spectacle, and taketh with the other. Earth has already lived through this once. Around 466 million years ago, our planet may have worn a ring of its own, and what happened during that brief geological episode left scars that are still readable in the rock today. 466 million years ago, the world was unrecognizable. The continents had not yet assembled into the shapes we know. Most of the planet's landmass was gathered in the southern hemisphere, clustered around a supercontinent called Gondwana that stretched from the South Pole to the tropics. North America, Europe, and fragments of Asia existed as scattered islands and microcontinents adrift in a vast global ocean. There were no trees, no grass, no flowers, no insects on land. The terrestrial surface was barren rock and sand, scoured by wind and rain with nothing to hold it in place. Life, almost all of it, was in the sea, and the sea was thriving. The Ordovician period, spanning roughly 485 to 443 million years ago, was one of the great expansions in the history of life on Earth. Marine biodiversity was exploding. Trilobites scuttled across the seafloor in hundreds of species, their calcite eyes scanning the water for food and predators alike. Brachiopods carpeted the shallow continental shelves in densities that rivaled modern coral reefs. Cephalopods, the ancestors of today's squid and octopus, cruised the open water in straight-shelled forms that could reach several meters in length, the apex predators of their age. Bryozoans, crinoids, graptolites, conodonts, the oceans were crowded with life in a way they had never been before. This was the world a rock from space was about to change. Somewhere in the inner solar system, an asteroid roughly 12.5 kilometers across, a rubble pile, loosely bound, held together more by friction and weak self-gravity than by solid cohesion, drifted into an orbit that brought it close to Earth. Not a direct hit. Not a screaming fireball tearing through the atmosphere and punching a crater into the crust. Something quieter than that, and in many ways, stranger. The asteroid crossed the Roche limit. At roughly 15,800 kilometers from Earth's center, tidal forces exceeded the asteroid's internal strength. The near side was pulled harder than the far side. Fractures opened, chunks broke free, and the body that had traveled millions of kilometers through interplanetary space as a single object came apart, silently, in the vacuum above the equator. Its fragments didn't fall, they spread. Each piece settled into its own orbit around the planet, and over weeks and months, collisions between those fragments ground the material finer, distributed it more evenly, and flattened the cloud of debris into a disk. Earth had a ring. This is the hypothesis published in 2024 by Andrew Tompkins and his colleagues at Monash University in Melbourne, Australia. Their paper, appearing in the journal Earth and Planetary Science Letters, didn't begin with asteroid dynamics or orbital mechanics. It began with a map of craters. 21 impact craters scattered across multiple continents: Sweden, Estonia, Russia, China, the United States, Australia, all dating to a narrow window within the Ordovician period. That alone was notable but not extraordinary. What was extraordinary was their distribution. Every single one of those 21 craters sat within 30 degrees of the equator. North or south, it didn't matter. None was found at high latitudes. None near the poles. All of them clustered in a belt wrapped around the planet's midsection. The researchers checked the math. More than 70% of Earth's continental crust during the Ordovician lay outside that equatorial band. If the impacts had been random, if they were caused by separate, unrelated asteroids arriving from different directions at different times, you would expect most craters to appear at higher latitudes, simply because that's where most of the target area was. The probability of all 21 falling within 30 degrees of the equator by chance alone came out to roughly 1 in 25 million. 1 in 25 million. To put that in perspective, it's like flipping a fair coin and getting heads 24 times in a row. It doesn't happen, not unless something is shaping the outcome. A ring shapes the outcome. Debris orbiting in the equatorial plane doesn't fall randomly across the globe. It spirals inward along orbital paths that intersect the atmosphere preferentially at low latitudes near the equator. A ring rains down on the tropics, and the craters it leaves behind cluster accordingly. The pattern Tompkins found is exactly what you would expect from a planet shedding ring material over millions of years, and the craters were not the only evidence. Throughout Ordovician limestone deposits in Europe, Russia, and China, geologists have found an unusual abundance of meteoritic material, tiny fragments of extraterrestrial rock embedded in sedimentary layers. These aren't rare. Micrometeorites fall on Earth constantly. What was unusual was the concentration. Certain Ordovician limestones contain meteoritic debris at levels far above the background rate, as though the planet were being dusted from above at an elevated pace for an extended period. The chemical signature of those fragments told a story of its own. Meteorites that travel through deep space for millions of years accumulate measurable levels of cosmic ray exposure, radiation damage that builds up over time and can be read like a clock. The Ordovician fragments showed low cosmic ray exposure, far less than you'd expect from rocks that had been drifting through the asteroid belt since the formation of the solar system. They hadn't been in space very long. They had been parked somewhere close, in orbit around the planet, shielded from the worst of the cosmic radiation by Earth's own magnetic field. Parked in a ring. The timeline Tompkins proposed runs roughly like this. Around 466 million years ago, a rubble pile asteroid broke apart at the Roche limit and formed a ring of debris above the equator. That ring persisted for somewhere between 20 and 40 million years, slowly losing material as particles spiraled inward and rained down through the atmosphere. The craters accumulated. The meteoritic dust settled into seafloor sediments, and the ring itself cast a shadow. We've already discussed what shadows do. This one did something historic. The late Ordovician saw the onset of the Hernantian Ice Age, one of the most severe glacial events in the last 500 million years. Global temperatures dropped by as much as 8 degrees Celsius. Ice sheets that had been confined to the South Pole expanded dramatically, reaching latitudes that hadn't seen ice in tens of millions of years. Sea levels fell as enormous volumes of water locked up in glaciers. Shallow continental shelves, the habitats where the overwhelming majority of Ordovician marine life lived, were exposed, drained, or buried under advancing ice. The result was catastrophic. The late Ordovician mass extinction, unfolding in two pulses separated by roughly 1 million years, wiped out approximately 85% of all marine species. Entire families of trilobites vanished. Brachiopod communities that had dominated the shallow seas for tens of millions of years were decimated. Graptolites, those tiny colonial organisms whose fossils are among the most common in Ordovician rocks, lost the majority of their species in what appears, in the fossil record, as a sudden and brutal pruning. The ring didn't act alone. No single factor ever drives a mass extinction by itself. Volcanic activity, changes in ocean chemistry, shifts in atmospheric carbon dioxide. All of these played roles that scientists are still working to disentangle. What the ring may have done is tip the balance. Earth's climate during the Ordovician was already trending cooler, moving from the greenhouse warmth of the early period toward the icehouse conditions of the late. The ring shadow, blocking sunlight across the tropics, reducing the solar energy reaching the surface, lowering temperatures just enough to push ice sheets past a critical threshold, may have been the nudge that sent the system over the edge. A nudge measured in degrees, a consequence measured in millions of extinct species. Not all scientists are convinced. Birger Schmitz, a geologist at Lund University in Sweden who has spent decades studying Ordovician meteorites, has called Tompkins's hypothesis a creative idea, while cautioning that the data are not yet sufficient to confirm it. The crater record is incomplete. Many Ordovician impact sites have been eroded, subducted, or buried under younger rock, which means the 21 craters we know about are almost certainly a fraction of the true total. Whether a more complete crater census would strengthen or weaken the equatorial clustering remains an open question. The meteoritic evidence, too, has alternative explanations. An unusually active period of asteroid breakups in the inner solar system, unrelated to a ring, could produce elevated meteorite flux without requiring debris to orbit Earth. And the correlation between the ring hypothesis and the Hernantian Ice Age, while compelling, is not yet a demonstrated causal link. Correlation and causation remain, as always, difficult to separate in deep geological time. What is not in dispute is that something unusual happened during the Ordovician. The craters are real. The meteoritic enrichment is real. The Ice Age is real. The extinction is real. Whether a ring connects them all is a question the next generation of research will have to answer, but the hypothesis fits the evidence in a way that no previous explanation has managed. Earth may have worn a ring for 20 to 40 million years. It was not a ring of ice, like Saturn's. It was rock and dust, dark and gritty, orbiting above the equator and slowly raining down onto a world that had no idea what was happening overhead. The creatures in the sea couldn't look up. They couldn't see the shadow. They could only feel it, in the cooling water, in the retreating shorelines, in the slow disappearance of the world they knew. The ring came and the ring went. The debris fell, the shadow lifted, and over millions of years the planet recovered. Life diversified again. New species filled the empty niches. The Silurian period that followed the Ordovician saw reefs return, fish diversify, and the first tentative colonization of land by plants and arthropods. Earth's ancient ring was temporary, a geological episode that lasted a few tens of millions of years before its debris rained down and vanished. What it left behind was written in limestone and crater rims, and the gaps in the fossil record where entire lineages simply stop. The question that lingers is different. What if the ring had never faded? What if it were permanent, a fixture of the sky as old as the oceans, as constant as the moon? What would a world like that look like after dark? For most of human history, night meant darkness, real darkness. The kind where you couldn't see your own hand in front of your face, where the only light came from the stars and the moon, where the boundary between the visible world and the invisible one was drawn by the sun's position below the horizon. Our ancestors lived inside that darkness for hundreds of thousands of years. They built fires against it. They told stories to fill it. They watched the Milky Way arc overhead, that faint, powdery band of 100 billion distant suns, and wove it into their mythologies, their religions, their sense of where they stood in the universe. On a ringed Earth, none of that would exist. The rings would catch sunlight long after the sun itself had set. High above the atmosphere, orbiting at thousands of kilometers, the ring particles would remain in direct sunlight for hours after the surface below had turned away from the sun and slipped into shadow. That reflected light, ring shine, would pour down onto the darkened landscape with a steady, diffuse glow that no amount of clouds, no season, no latitude could fully escape. The brightness would vary. Near the equator, where you see the rings edge on, ring shine would be at its weakest. The narrow line of the ring simply doesn't present enough reflective surface to flood the sky. At mid-latitudes, where the rings spread into a broad arch occupying a significant portion of the sky, the glow would intensify dramatically. A clear night in Istanbul or New York or Buenos Aires with no moon in the sky could be brighter than a full moon night on our current Earth. Not the harsh brightness of a street lamp, something softer, a cool, even illumination that erased the deepest shadows without creating sharp ones of its own, as though the entire sky were glowing faintly from within. The Milky Way would vanish, not gradually, not partially, completely. That delicate river of starlight is only visible when the sky is truly dark, when no competing light source washes out the faintest photons arriving from 100,000 light-years away. On our Earth today, light pollution has already hidden the Milky Way from more than a third of humanity. A study published in the journal Science in 2023 found that the night sky is brightening at a rate that effectively doubles its luminosity every 8 years, driven by the spread of artificial lighting. Billions of people alive today have never seen the Milky Way with their naked eyes. Rings would finish the job. Even in the most remote wilderness, far from any city or road or electrical grid, the rings would pour enough reflected sunlight onto the atmosphere to wash out all but the brightest stars. You would still see Jupiter, Venus, Mars, Sirius, a handful of the most luminous points in the sky. Everything else, the constellations in their full detail, the Andromeda Galaxy as a faint smudge, the zodiacal light, the meteor showers that streak across a black canvas, would be lost behind a permanent veil of ring shine. Think about what that means for a species that spent most of its existence navigating by stars. The constellations that shaped human culture, Orion, Ursa Major, the Southern Cross, Scorpius, would be dramatically diminished. You might still pick out their brightest stars on an exceptionally clear night, but the full patterns, the shapes that ancient Greeks and Egyptians and Polynesians traced across the darkness, would be difficult or impossible to see. Constellation mythology would be thinner, simpler, built around a handful of brilliant points rather than elaborate figures connecting dozens of faint ones. The sky stories that filled libraries and temples across the ancient world would be smaller stories, told about fewer stars. The star that might suffer most is the one you'd think would be safest. Polaris, the North Star, the fixed point around which the northern sky appears to rotate, is not actually very bright. It sits at roughly the 50th brightest star in our sky, easily overlooked even on a moderately lit night. Under ringshine, Polaris could disappear entirely for observers at many latitudes, drowned in the ambient glow. Northern Hemisphere civilizations that relied on it for navigation, Vikings, Arab traders, Pacific Islanders crossing open ocean, would need to find another reference point. They would have one, the rings themselves. The rings sit above the equator. Always. They don't migrate with the seasons, don't shift with the years, don't wobble or drift. From anywhere in the Northern Hemisphere, the rings arc across the southern sky. From anywhere in the southern hemisphere, they arc across the northern sky, and the height of that arc above the horizon tells you, with rough but reliable accuracy, how far you are from the equator. A high arch means you're in the mid-latitudes. A low hump near the horizon means you're approaching the poles. A vertical line overhead means you're standing on the equator itself. The rings wouldn't just replace the stars as a navigational tool. In some ways, they'd be better. Stars require clear skies, knowledge of which constellation is visible in which season, and the ability to distinguish faint points of light from one another. The rings require only that you look up. They are visible through thin clouds, through haze, through the kind of atmospheric murk that would render stars invisible. They are the same every night. They don't change with the seasons. They are, in the most literal sense, a compass written across the sky. We'll explore the full implications of that compass in the next chapter. For now, the point is this: the loss of the dark sky would not leave humanity without celestial guidance. It would replace one system with another, trading the complexity and subtlety of stellar navigation for the brute simplicity of a luminous band that never moves. The deeper consequence of perpetual ringshine lies not in navigation, but in perception. Darkness shapes the human mind in ways we rarely think about. The circadian rhythm, that internal clock governing sleep, wakefulness, hormone production, and mood, is calibrated to the cycle of light and dark. Melatonin, the hormone that triggers sleepiness, is produced by the pineal gland in response to darkness. Bright light suppresses it. Dim light allows it. The transition from day to night, from brightness to blackness, is the signal that tells your body to prepare for rest. Under rings, that signal weakens. The night never fully darkens, the sky never fully turns off, and the body's expectation of blackness, an expectation wired into our biology by hundreds of millions of years of evolution, is never entirely met. The effects wouldn't be dramatic in the way a shadow-induced ice age is dramatic. They would be subtle, chronic, woven into the fabric of daily life. Slightly disrupted sleep, slightly altered hormone cycles, a faint but persistent sense that something about the night isn't quite right, even if you've never known it any other way. Animals would feel it too. Sea turtle hatchlings, which navigate to the ocean by crawling toward the brightest horizon, typically the moonlit sea, would face a sky where every direction glows. Migratory birds that orient themselves by star patterns would lose their celestial map. Nocturnal predators that depend on darkness for hunting would find themselves perpetually exposed, their camouflage undermined by a sky that never quite cooperates. Coral spawning, firefly mating, bat foraging, dozens of biological processes timed to darkness would be disrupted by a light source that no curtain can block and no season can silence. The night, as a concept, would still exist. The sun would still set. Clocks would still mark the hours. People would still sleep, still dream, still close their eyes and wait for morning. What would be missing is the quality of the darkness between those moments, the depth of it, the completeness of it, the ancient primal blackness that once forced our ancestors to sit still, listen to the world, and wonder what was out there. On a ringed Earth, the answer would always be visible. The rings would glow overhead, patient and constant, offering light where there used to be mystery and guidance where there used to be stars. And for a species that learned to sail oceans by reading the patterns of faint light in a dark sky, the presence of those rings overhead would reshape not just how we see the night, but how we cross it. Long before compasses, before sextants, before GPS satellites beaming signals from 20,000 kilometers overhead, humans crossed oceans by reading the sky. Polynesian navigators sailed thousands of kilometers across the open Pacific, using nothing but the positions of stars, the patterns of ocean swells, and the flight paths of birds. Phoenician traders steered by Polaris and the constellation Ursa Minor along the Mediterranean coast. Arab sailors measured the altitude of known stars above the horizon with a wooden instrument called a kamal, a small card held at arm's length, its distance from the eye calibrated to give a rough latitude reading. Vikings, according to saga tradition, may have used sunstones, translucent crystals of calcite that polarize light, to locate the sun's position on overcast days when no stars were visible. All of these methods share a common requirement. They need the sky to cooperate. They need clear nights, identifiable stars, and enough darkness for those stars to stand out against the background. Take away the darkness, wash out the faint stars with a permanent source of ambient light, and the entire system begins to break down. A Polynesian wayfinder who couldn't see the lower magnitude stars in his mental star compass would be missing half his map. A Viking navigator searching for Polaris through a sky bright with ring shine might never find it at all. The rings would break one navigational system and replace it with another. And the replacement, in certain respects, would be simpler. The principle is rooted in geometry. Earth's rings orbit above the equator, fixed in the equatorial plane, and their apparent position in the sky depends entirely on the observer's latitude. This relationship is direct, consistent, and requires no knowledge of astronomy to exploit. You don't need to memorize the names of stars. You don't need to know what month it is. You don't need instruments. You just need to look up and note where the rings sit relative to the horizon. At the equator, the ring appears as a thin, bright line passing directly overhead, from the east horizon through the zenith to the west horizon. As you move north, that line drops southward and opens into an arch. At 10 degrees north, the arch peaks at roughly 80 degrees above the southern horizon. At 30 degrees north, it peaks at about 60 degrees. At 45 degrees, the ring's highest point sits at roughly 45 degrees above the southern horizon, halfway between zenith and the ground. At 60 degrees north, the arch has flattened to a low curve barely 30 degrees above the horizon. At the poles, the rings would skim the horizon line, a faint glow along the edge of the world. This gradient is smooth, predictable, and identical on every clear night for the rest of the planet's existence. A sailor in the open Atlantic who knew this relationship, who had memorized or carried a simple table showing the ring's maximum altitude for each degree of latitude, could determine his north-south position with reasonable accuracy simply by measuring the angle of the ring's peak above the southern horizon. No clock required, no star chart, no clear view of the full sky. Just the ring, which is visible through haze, through thin clouds, through conditions that would render stellar navigation useless. The east-west component is harder. Rings don't help with longitude. They are symmetric around the equator, so a sailor at 40 degrees north and 30 degrees west sees the same ring geometry as a sailor at 40 degrees north and 90 degrees east. This is the same problem that plagued real-world navigation for centuries. Latitude was always the easy measurement, the altitude of Polaris, the sun's noon angle, and now the ring's peak altitude all give it directly. Longitude required something latitude methods couldn't provide, an accurate clock. Knowing what time it is in a reference location while observing what time it appears to be locally allows you to calculate the angular difference between the two, and that angular difference is your longitude. On our Earth, the longitude problem wasn't reliably solved until John Harrison built his marine chronometer in the 1760s, more than 2 centuries after European navigators began crossing the Atlantic with essentially no accurate way to determine east-west position. On a ringed Earth, the timeline might be different. The ease of latitude determination could have focused intellectual energy earlier on the remaining unsolved problem, longitude, potentially accelerating the development of precision timekeeping. Or it might not have. The relationship between technological ease and innovation is never straightforward. Sometimes solving the easy problem first makes people complacent about the hard one. What the rings would unquestionably change is the accessibility of navigation itself. In our world, celestial navigation was an elite skill. It required years of training, memorization of star catalogues, familiarity with seasonal sky changes, and the ability to perform mental trigonometry under the rolling, pitching conditions of a ship at sea. Not every sailor could do it. On many vessels, only the captain or navigator possessed the knowledge, and if that person died or was incapacitated during a voyage, the ship could be lost. Ring navigation, by contrast, would be democratic. The ring is one object, always in the same place, always visible. A child could learn the basic principle in an afternoon. The higher the ring, the closer you are to the equator. The lower the ring, the farther you are from it. Fishermen, coastal traders, anyone who ventured out of sight of land would carry this knowledge instinctively, the way we instinctively know that the sun rises in the east. It would be part of the shared baseline understanding of the world, not specialized knowledge, but common sense. This democratization could have reshaped the age of exploration. In our history, European maritime expansion was constrained not just by ship technology and political will, but by the availability of skilled navigators. Portugal, Spain, England, and the Netherlands poured resources into training navigators and developing instruments precisely because ocean crossing required expertise that was scarce and expensive. On a ringed Earth, the navigational barrier to open ocean voyaging would be lower, not eliminated. You still need seaworthy ships, provisions, favorable winds, and the courage to sail beyond the horizon, but meaningfully reduced. Whether this would have led to earlier transoceanic contact, different patterns of colonization, or a broader distribution of maritime power among civilizations is impossible to say with certainty. What can be said is that the barrier would have been shaped differently, and the history that followed would have been shaped differently along with it. The rings would have influenced movement on land as well, though less dramatically. Overland travelers rarely face the same directional uncertainty as sailors. Landmarks, roads, rivers, and mountain ranges provide orientation that open ocean does not. Still, in featureless terrain, deep desert, Arctic tundra, open steppe, the rings would serve the same function they serve at sea. Caravans crossing the Sahara or the Central Asian grasslands would have had a permanent celestial reference visible even on moonless nights, reducing the risk of disorientation in landscapes where every dune and every hilltop looks the same. And there is one more navigational consequence worth considering, though it belongs more to the realm of cartography than seamanship. The rings would have provided humanity with a visible, physical marker of the equator, the one line of latitude that corresponds to a directly overhead ring viewed edge-on. Every other latitude line is an abstraction, a mathematical construct drawn on maps and globes. The equator, on a ringed Earth, would be the latitude where the ring passes through the zenith. You could stand there and point straight up and say, with absolute certainty, that is the middle of the world, not because a map tells you so, because the sky tells you so. That kind of certainty, a geographic truth written in light rather than ink, would have been profoundly meaningful to civilizations trying to understand the shape and structure of their world. And it would have been only one of many ways the rings reshaped how humans thought about the sky, the earth, and the relationship between them. The rings wouldn't just guide explorers across the oceans. They would reshape the very civilizations those explorers came from, their religions, their architecture, their art, and their deepest beliefs about the nature of the cosmos. Because a permanent, luminous structure spanning the sky is not something any human culture could ignore. It would become the center of everything. Every civilization that has ever looked up has seen meaning in what it found there. The Egyptians watched Sirius rise just before dawn each July and knew the Nile flood was coming. So they made Sirius sacred, tied it to the goddess Isis, and built an entire agricultural calendar around a single star's annual appearance. The Mesopotamians tracked the movements of Venus across the evening and morning sky and named it Ishtar, goddess of love and war, because the planet's pattern, appearing, vanishing, reappearing on the other side of the sun, seemed to embody death and resurrection. The Maya watched the Milky Way rotate through the night and saw in its pale band a great world tree connecting the underworld to the heavens, its roots in the south, its branches reaching north. The Greeks populated the sky with heroes and monsters, tracing the outlines of their myths across the constellations and using those myths to teach navigation, agriculture, and morality to every generation that followed. All of these were responses to a sky full of small, scattered, moving points of light. Stars drift, planets wander, the moon changes shape, the sun marches along the ecliptic through the year. Each of these motions invited interpretation, and each civilization interpreted them differently, filtering the sky through its own history, geography, language, and fears. Now put a ring in that sky, not a point of light, not a wandering dot. A permanent, massive, luminous arch spanning the heavens from horizon to horizon, visible every single night and most days, unchanging in position, undeniable in presence. It would be the largest thing any human being had ever seen. Larger than any mountain, larger than any ocean viewed from shore, larger than the moon by orders of magnitude in apparent size. And unlike the stars, it would demand no specialized knowledge to observe. A newborn infant, opening its eyes for the first time, could see it. No mythology on Earth would be unaffected. No religion would fail to address it. No creation story would be told without it. The specific interpretations would differ by culture, latitude, and era, just as they differ for the sun, moon, and stars in our own history. A civilization at the equator, seeing the ring as a thin vertical line splitting the sky in two, might interpret it as a cosmic boundary, the seam where the gods divided the world during creation, the edge where the realm of the living meets the realm of the dead, a wall of light separating one half of existence from the other. A civilization at mid-latitudes, seeing the ring as a great arch sweeping across the southern sky, might see a bridge, a path the gods walk between heaven and earth, a road for the souls of the dead traveling to the afterlife, a physical manifestation of the connection between the mortal world and the divine one. The Norse had Bifrost, a rainbow bridge connecting Midgard, the world of humans, to Asgard, the realm of the gods. In our world, Bifrost was an occasional phenomenon, visible only when rain and sunlight conspired to create it. On a ringed Earth, the bridge would be permanent. It would be there every night, glowing, immovable, stretching across the sky with a solidity no rainbow could match. Bifrost wouldn't be a fleeting gift from the gods. It would be the defining feature of the cosmos. Other mythological frameworks might interpret the ring differently. A creation myth might describe the ring as the remnant of a cosmic act, the debris left behind when a god shaped the earth, the shavings from the lathe on which the world was turned. A moral framework might see the ring as a divine eye, an ever-present watcher in the sky that sees all human action and judges accordingly, a celestial conscience that cannot be escaped because it never sets, never blinks, never looks away. A dualistic religion might split the ring into light and dark halves, the illuminated face representing goodness and truth, the shadowed face representing sin and corruption, and build an entire ethical system around which side of the ring faces the sun in a given season. None of these are predictions. They are extrapolations from what we know about how human cultures respond to persistent, visible, unexplained features of the natural world. And the rings would be the most persistent, most visible, and, for most of human history, most unexplained feature imaginable. Architecture would follow mythology, as it always has. Temples, pyramids, and cathedrals in our world are frequently aligned to astronomical events: the solstice sunrise, the equinox sunset, the heliacal rising of a particular star. On a ringed Earth, the ring itself would become the primary axis of alignment. Sacred buildings would be oriented toward the point where the ring crosses the horizon. Doorways and windows would frame the ring's arch at specific times of day. Altars would be placed beneath openings that allowed ring light to fall on them during ceremonies. The relationship between architecture and sky that produced Stonehenge, the pyramids of Giza, and Angkor Wat would, on a ringed Earth, produce structures aligned not to the solstice sun or the rising Pleiades, but to the ring. Calendars, too, would be reshaped. The ring's brightness changes through the year as the sun's angle relative to the ring plane shifts with the seasons. The equinox brightening, that dramatic flare as sunlight streams edge on through the ring, would be among the most conspicuous, regular astronomical events visible from the surface. Cultures would mark it, celebrate it, fear it, or worship it, depending on their relationship to the sky. Spring planting festivals, harvest rituals, New Year celebrations, Many of these could anchor to the ring's equinox brightening, rather than the solstice or the lunar cycle that anchors so many real-world calendars. The ring shadow's seasonal migration, northward in one half of the year, southward in the other, would provide another calendrical marker, particularly for civilizations living in the shadow zone. The arrival and departure of the shadow, bringing cooler temperatures and reduced sunlight, would be as significant as the onset of the rainy season in monsoon-dependent cultures today. Shadow festivals, shadow fasts, shadow pilgrimages to latitudes where the shadow falls latest or not at all. The ring's physical effects on climate and light would intertwine with its spiritual significance until the two became inseparable. And art. From the earliest cave paintings at Lascaux and Altamira, humans have depicted what they see in the world around them. Animals, hands, hunting scenes, abstract symbols. The sky appears rarely in prehistoric art, but the ring would not be a subtle feature easily overlooked by a painter working by firelight on a cave wall. It would be the most visually dominant feature of the nighttime world, a glowing arch visible from the mouth of every cave, and its absence from cave art would be stranger than its presence. Rings would appear in the earliest human artistic records. They would be painted, carved, woven into textiles, cast in bronze, chiseled into temple walls. The arch motif, a sweeping curve from one side of a surface to the other, would be one of the foundational symbols in human visual culture, as ubiquitous as the circle of the sun or the crescent of the moon. Music might carry the ring's influence too, though more abstractly. Songs about the ring, hymns to it, lullabies that reference its glow as a source of comfort in the night. These would be as natural as songs about the moon or the stars in our own tradition. The ring's constancy, its refusal to set or fade, would lend itself to themes of permanence, watchfulness, protection, and eternity. Love songs would invoke it, funeral dirges would reference it, anthems of war and peace alike would draw on its imagery, because the ring would be the one thing every human on the planet shared, regardless of language, geography, or era. The philosophical implications would run deeper still. In our world, the question, "Why are we here?" has driven human thought for millennia, and the sky, vast, silent, mostly empty, has often served as the backdrop against which that question is asked. A ringed sky is not empty. It has a structure, an object, a thing that invites not just wonder but explanation. Why is the ring there? Is a question a child asks, and it is also a question that would have driven the earliest natural philosophers toward what we would eventually call science. The ring demands an explanation, and the search for that explanation, what is it made of? Why doesn't it fall? How did it get there? Would have shaped the trajectory of human inquiry from its earliest beginnings. Mythology would eventually give way to observation, observation to hypothesis, and hypothesis to the systematic investigation of the natural world. And when the first telescopes turned toward the rings, what they revealed would challenge everything people thought they knew about the arch that had hung above them since before memory began. For tens of thousands of years, the rings would have been a mystery, a permanent fixture of the sky with no obvious explanation, no visible mechanism, no analogy in everyday experience. Rocks fall, water flows downhill, smoke rises. Everything in the human world either moves toward the ground or drifts away from it. The rings did neither. They hung there, motionless, luminous, seemingly weightless, defying the most basic intuition about how objects behave. For most of human history, the only available explanation would have been the one every culture reached for when confronted with the inexplicable. The gods put it there. The first crack in that explanation would have come not from studying the rings themselves, but from studying everything else. The slow accumulation of astronomical knowledge, the tracking of planetary motions, the measurement of solar and lunar cycles, the development of geometric models to predict eclipses, would have gradually built a framework within which the rings could be reconsidered. Not as a divine artifact, but as a natural phenomenon obeying the same rules as the moon, the planets and the falling apple. The turning point, as in our own history, would likely have been the telescope. When Galileo pointed his instrument at the moon in 1609 and saw mountains and craters, a landscape, not a smooth celestial sphere, he shattered the ancient idea that heavenly bodies were fundamentally different from earthly ones. On a ringed Earth, the first telescopic observations of the rings would have been equally revolutionary, because through a telescope, the rings would not look like a solid band. They would look like what they are, a swarm. Millions of individual points of reflected light, each one a separate particle, each one in its own orbit, the entire structure resolving from a smooth arch into a vast, grainy cloud of orbiting debris. That single observation, the rings are not solid, would have been the most important astronomical discovery in this alternate history. It would have demolished any remaining notion that the rings were a divine construction, a cosmic bridge, or a wall between worlds. They were rubble, orbiting rubble, and the question that followed would have reshaped natural philosophy. What keeps the rubble up? The answer, when it came, would have arrived along the same intellectual path it followed in our world. Isaac Newton, or someone like him, would have formulated the laws of gravitation and orbital mechanics that explain how a particle can fall toward a planet endlessly without ever reaching the surface, because its sideways velocity carries it around the curve of the planet as fast as gravity pulls it down. Every ring particle is falling, every single one. They are all in a perpetual state of free fall, tracing elliptical paths around the Earth at speeds that precisely balance the gravitational pull, trying to drag them to the surface. The rings don't defy gravity. They are gravity's most elegant demonstration. On our Earth, Newton's laws were tested against the motions of the Moon and the planets, distant objects whose orbits could be calculated but not easily visualized. On a ringed Earth, the proof would have been overhead every night. The rings would have been a laboratory, a visible, tangible demonstration of orbital mechanics operating in real time. Students learning about gravity wouldn't need to imagine elliptical orbits around an abstract point. They could step outside and see billions of objects executing those orbits simultaneously, all of them obeying the same simple equations that governed the fall of a stone dropped from a tower. The Scottish physicist James Clerk Maxwell provided another crucial insight in our own timeline, one that would have been equally necessary on a ringed Earth. In 1857, Maxwell proved mathematically that Saturn's rings could not be solid. A rigid disk orbiting a planet would experience different gravitational forces at different distances from the center, the inner edge being pulled harder than the outer edge, and those differential forces would tear any solid structure apart. The rings had to be composed of independently orbiting particles, each following its own Keplerian orbit, the inner ones moving faster than the outer ones, the whole assembly maintaining its shape not through structural integrity, but through the statistical behavior of countless individual objects. This insight, that structure can emerge from chaos, that a flat, organized disk can arise from nothing more than gravity and collisions acting on a swarm of debris, would have been philosophically profound on a ringed Earth. The most visually ordered feature of the sky, the great arch that inspired temples and creation myths, would turn out to be nothing but a crowd of rocks, each one ignorant of the others, each one simply falling around the planet in its own private orbit. Order from disorder, pattern from randomness. It's a theme that runs through modern physics, from thermodynamics to galaxy formation, and on a ringed Earth, the first and most vivid example of it, would have been hanging in plain sight for all of human history. The composition of the rings would have been the next puzzle. In our world, spectroscopy, the analysis of light split into its component wavelengths, revealed that Saturn's rings are made primarily of water ice. On a ringed Earth, the same technique would have shown something different. Silicates, iron oxides, carbon compounds. Rock. The rings would have been identified as mineral debris, chemically similar to asteroids and meteorites, and this would have raised an immediate question. Where did the rock come from? The answer would have led straight to the Roche limit. Edouard Roche's 1848 calculation, defining the distance within which tidal forces overpower a body's self-gravity, would have been not just an interesting theoretical result, but a direct explanation for the most prominent feature of the sky. The rings exist because something crossed that invisible boundary and was destroyed. The mathematics of tidal disruption, which on our Earth remained a somewhat abstract branch of celestial mechanics, would have been central to the scientific understanding of a ringed planet. Every educated person would have known the Roche limit the way every educated person on our Earth knows the speed of light, as a fundamental constant of the world they live in. Dating the rings would have been contentious. Are they as old as the planet, or did they form later? The debate would have mirrored the one that raged over Saturn's rings in our own timeline, a debate that wasn't settled until Cassini's final measurements in 2017 revealed that Saturn's rings are surprisingly young. On a ringed Earth, the tools for answering the question would have been different. Geologists, rather than spacecraft engineers, would have led the investigation. The meteoritic debris raining down from the ring would have been collected, analyzed, and dated using radiometric techniques. The cosmic ray exposure ages of ring-derived meteorites, short exposure times indicating the material hadn't been in space very long before being captured into orbit, would have provided clues about when the ring formed. Whether that investigation pointed to an ancient origin or a more recent one would have depended on the actual history of the ring, which we're leaving deliberately open. What matters is the trajectory of inquiry itself, from mythology to observation, from observation to mathematics, from mathematics to a physical understanding of a structure that had been worshipped for millennia. The same intellectual progression that took humanity from astrology to astronomy in our world would have played out on a ringed Earth, driven by the same curiosity but focused on a far more dramatic target. And that understanding would have brought with it a sobering realization. The rings are not eternal. They are a dynamic system, constantly evolving, losing material to atmospheric drag and gravitational perturbation, grinding themselves finer through collisions, slowly dissipating over geological time. The great arch that inspired religions and guided sailors would have been revealed by the very science it helped inspire as temporary, beautiful, ancient, magnificent, and doomed. That realization, and its implications for climate, would have pushed the scientific community toward a deeper investigation of what the rings were doing to the planet beneath them. We touched on the ring shadow earlier in broad strokes, how it moves with the seasons, how it cools the hemisphere it falls on, how it might have contributed to the Ordovician Ice Age. Now it's time to look closer. Because on a planet where rings are permanent, the shadow isn't an occasional disruption. It's a feature of the climate system, as fundamental as the tilt of the axis or the circulation of the oceans. Every weather model, every agricultural calendar, every decision about where to build a city or plant a crop would have to account for a band of reduced sunlight that sweeps across the planet twice a year and never fully goes away. The mechanics bear repeating in finer detail. The rings orbit in the equatorial plane. The Sun, as seen from Earth, moves north and south of that plane over the course of a year, reaching its northernmost point at the June solstice and its southernmost at the December solstice. When the Sun is north of the ring plane, it illuminates the rings from above and the shadow falls south. When the Sun is south, the shadow falls north. At the equinoxes, the Sun sits almost exactly in the ring plane and the shadow falls on the equator itself. A narrow, intense band of shade draped across the tropics like a belt cinched around the planet's waist. The width of that shadow on the ground depends on the physical width of the ring and its distance from the surface. A ring extending from 9,500 to 18,000 kilometers above the equator, the approximate Roche limit zone, would cast a shadow that varies from a few hundred kilometers wide at the solstices, when the Sun strikes it at a steep angle, to potentially 1,000 kilometers or more at the equinoxes, when the geometry aligns to project the ring's full width onto the surface. The shadow's edges would not be sharp. Ring particles are not a solid sheet, but a diffuse swarm, and the shadow they produce would be a gradient. Deep shade at the center, fading to a penumbral dimming at the edges with dappled patches of full sunlight leaking through gaps in the ring's structure. This is not the crisp, clean shadow of a solar eclipse. It is something stranger and more persistent. A region of reduced light that covers hundreds of thousands of square kilometers and lingers for weeks or months as it migrates across latitudes, arriving like a slow tide of dimness that darkens the sky without blackening it, cools the air without freezing it, and alters the rhythm of the day without stopping it. For the climate system, the critical variable is energy. Earth's climate is driven by solar energy absorbed at the surface and redistributed by the atmosphere and oceans. Anything that reduces the amount of energy reaching the surface, volcanic aerosols, changes in cloud cover, variations in Earth's orbit, produces cooling. The ring shadow reduces surface energy input in a geographically targeted way, creating bands of relative cooling that shift with the seasons and concentrate at the equator during the equinoxes. The global average temperature reduction from a moderately dense ring, something thick enough to block perhaps 20 to 40% of incoming sunlight along its shadow path, could be somewhere between 1 and 3 degrees Celsius. That number, as we discussed earlier, sounds modest until you recall that the entire difference between the current climate and the last glacial maximum is only 5 to 6 degrees. A 2-degree cooling from a permanent ring shadow would not plunge the planet into an ice age on its own, but it would shift every thermal boundary on Earth by several hundred kilometers toward the equator. The tree line would drop. The permafrost boundary would advance. Deserts that currently sit at the edge of the tropics might receive enough additional moisture from altered circulation patterns to green slightly, while forests at higher latitudes might thin as growing seasons shorten and winter temperatures intensify. The tropics would feel the effect most acutely, and that is deeply consequential because the tropics are the engine of Earth's climate. Warm equatorial waters evaporate, rise, release their moisture as rain, and drive the great convective cells, the Hadley cells, that circulate air between the equator and roughly 30 degrees latitude in both hemispheres. Reduce the solar heating at the equator even periodically, and the Hadley circulation weakens. Weaker Hadley cells mean less moisture transport, less tropical rainfall, and a contraction of the intertropical convergence zone, the band of heavy precipitation that migrates north and south with the seasons and delivers the monsoon rains that sustain billions of people across South Asia, West Africa, and Central America. A permanent ring on Earth would, in effect, install a dimmer switch on the tropical engine, not an off switch. The sun still shines, the tropics are still warm, and the Hadley cells still circulate. The dimming is partial and periodic, but partial and periodic is enough to matter when the systems involved operate at planetary scale, and the populations depending on them number in the billions. The equinox shadow deserves special attention. Twice a year, for roughly 2 to 3 weeks centered on the vernal and autumnal equinoxes, the ring shadow falls directly on the equatorial band. This is the densest shadow, the most direct blocking of sunlight, concentrated on the latitudes that are ordinarily the warmest on the planet. The Amazon basin, the Congo, the Indonesian archipelago, the maritime corridor of Southeast Asia, all would experience a noticeable dip in solar radiation during these periods. Cloud formation patterns would shift. Thunderstorm activity, which in the deep tropics is driven largely by surface heating, would decrease. Rainfall totals for the equinox months would be lower than they would otherwise be on an unringed Earth. For ecosystems tuned to the rhythms of equatorial climate, even small perturbations can cascade. Tropical rainforests, despite their apparent lushness, exist in a surprisingly delicate balance between rainfall and evapotranspiration. Reduce rainfall by 10 or 15% during 2 critical months of the year, and the forest doesn't collapse immediately, but it thins at the margins. Drier edges recede. Savanna pushes inward. Over thousands of years, the boundary between forest and grassland shifts, and with it the carbon storage capacity of the biosphere, the habitat available to millions of species, and the regional water cycle that depends on the forest itself to generate a significant fraction of its own rainfall through transpiration. Ocean currents, driven by temperature and salinity gradients, would adjust to the new thermal regime. The thermohaline circulation, that deep, slow conveyor of cold water sinking at high latitudes and flowing along the ocean floor toward the equator, where it warms, rises, and returns along the surface, responds to changes in the temperature differential between poles and tropics. A ring-cooled tropics and ring-shadowed mid-latitudes would reduce that differential in some seasons and enhance it in others, creating an oscillating perturbation in a system that already exhibits complex, non-linear behavior. Predicting the exact outcome is beyond current modeling capability, but the general principle is clear. The thermohaline circulation would not remain unchanged, and its changes would ripple through marine ecosystems, fisheries, and coastal climates on every continent. And then there is ice. The polar regions receive the least direct effect from the ring shadow. The shadow barely reaches high latitudes, and the rings themselves sit low on the horizon as seen from the poles. The cooling that matters for ice sheets is indirect. Lower global temperatures mean less heat transported poleward by both atmospheric and oceanic circulation. Ice that melts each summer melts a little less. Ice that forms each winter forms a little more. The imbalance is tiny on any given year, but cumulative over centuries and millennia. Permanent rings would bias the planet toward a colder state. Not dramatically, not catastrophically in most scenarios, but persistently. A ringed Earth would spend more of its time in glacial or near-glacial conditions than our unringed Earth does, and the warm, interglacial periods that our civilization grew up in would be shorter, cooler, and more precarious. In 2005, a team of engineers published a paper in Acta Astronautica proposing, remarkably, that humanity should build a ring around Earth on purpose. The idea, authored by Jerome Pearson and colleagues, envisioned a band of small particles or reflective satellites orbiting at 1.2 to 1.6 Earth radii, positioned to shade the tropics and reduce the solar energy driving global warming. The estimated cost ranged from $6 trillion to $200 trillion for a particle ring, or $125 to $500 billion for a network of small satellites. The side effect, the authors noted almost in passing, would be a night sky permanently as bright as a full moon. It was an audacious proposal, and it remains firmly in the realm of the theoretical. What it illustrates is the double-edged nature of the ring's climate effects. Shade the tropics, and you cool the planet, but you also disrupt monsoons, alter rainfall, stress ecosystems, and eliminate the dark sky. The same physics that could theoretically offset global warming could also destabilize the agricultural systems that feed a significant fraction of humanity. The rings would not be a catastrophe. They would be a condition, a permanent modification to the planet's energy budget that every living system, from phytoplankton to civilizations, would have to absorb and adapt to. Some regions would benefit. Higher latitudes with harsh winters might see little change, or even slight warming from altered circulation. Other regions, the monsoon-dependent tropics, the semi-arid margins, the coral reef systems already stressed by temperature variability, would bear the cost. The rings would reshape the climate the way a dam reshapes a river. Not by stopping the flow, but by changing its character, where the water goes, how fast it moves, what lives in it, and what grows along its banks. The planet would still function, life would still thrive. The question is whether our particular civilization, built on assumptions about a climate that no longer holds, could thrive along with it. And there is a further complication, one that has nothing to do with shadow or temperature, but everything to do with the space above the atmosphere. because the same ring that shadows the surface also occupies the orbital corridors that modern civilization depends on for communication, navigation, and the ability to leave the planet at all. The first rockets in human history were Chinese fire arrows, bamboo tubes packed with gunpowder and aimed at enemy fortifications during the Song dynasty, nearly 1,000 years ago. They flew a few hundred meters at most, arcing briefly above the battlefield before plunging back to Earth. No one watching them could have imagined that the same basic principle, controlled combustion producing thrust, would one day carry human beings into orbit and beyond. The journey from those bamboo tubes to the Saturn V rocket that launched Apollo 11 required 9 centuries of incremental progress in chemistry, metallurgy, aerodynamics, and mathematics, all converging on a single goal: escaping the planet's gravitational pull long enough to reach the emptiness above. On a ringed Earth, the emptiness above would not be empty. The ring occupies a band of orbital space stretching from roughly 9,500 kilometers to 18,400 kilometers above the equator, the zone defined by the Roche limit, where tidal forces prevent debris from coalescing into a moon. This places the ring squarely in the region between low Earth orbit and medium Earth orbit, straddling 2 of the most important corridors in the architecture of modern spaceflight. Low Earth orbit, the zone from the surface up to about 2,000 kilometers, sits below the ring. This is where the International Space Station flies, at roughly 400 kilometers. It's where most Earth observation satellites operate, where the Hubble Space Telescope orbits, and where crewed spaceflight has spent the vast majority of its history. Below the ring, this zone remains accessible. Rockets launched into low-inclination orbits that stay well beneath the ring's inner edge could reach this space without crossing the debris field. The ISS in this scenario could exist. Geostationary orbit, the band at 35,786 kilometers, where a satellite's orbital period matches Earth's rotation, allowing it to hover over a fixed point on the equator, sits above the ring. This is where most communications satellites and many weather satellites operate. It too could be reached, but only by passing through the ring on the way up. And that is the problem. The ring particles are not stationary. They orbit at speeds determined by their altitude, faster at the inner edge, slower at the outer. At 9,500 kilometers, orbital velocity is roughly 6.3 kilometers per second. At 18,000 kilometers, it drops to about 5.4. A rocket ascending through the ring plane would encounter particles moving at these speeds, and the relative velocity between the rocket and the debris could easily reach several kilometers per second, depending on the trajectory. At those speeds, a particle the size of a pea carries the kinetic energy of a bullet. A particle the size of a marble carries the energy of a hand grenade. A fist-sized chunk of rock, striking a spacecraft at 5 kilometers per second, would punch through the hull like a cannonball through plywood. This is not a hypothetical risk. It is the central engineering challenge of spaceflight on a ringed Earth. Every mission that needs to reach geostationary orbit, every spacecraft bound for the Moon, every probe heading to Mars or Jupiter or beyond, all of them must cross the ring plane. And the ring plane is a kill zone. The numbers that describe our current orbital debris problem offer some perspective, though the ring would dwarf them. As of today, tracking networks monitor roughly 34,000 pieces of debris larger than 10 centimeters in low Earth orbit. An estimated 900,000 fragments between 1 and 10 centimeters are up there as well, too small to track reliably, but large enough to disable a satellite or puncture a spacecraft hull. These numbers are growing, and the fear of a cascading chain reaction, one collision producing debris that causes more collisions, which produce more debris, which cause more collisions, has a name: the Kessler syndrome, after NASA scientist Donald Kessler, who described the scenario in 1978. A ring is a natural Kessler state. It is a self-sustaining field of debris in which collisions are constant, fragments are continuously generated, and the density of material is maintained by the ongoing grinding of particles against one another. The ring doesn't threaten to become a debris field, it is a debris field. It has been one since it formed, and it will remain one until it dissipates. Launching through it would require one of two strategies: avoidance or armor. Avoidance means finding gaps. No ring is perfectly uniform. Saturn's rings are full of divisions. The Cassini division, the Encke gap, the Colombo gap, cleared by the gravitational influence of embedded moonlets or resonance effects with larger moons. A ring around Earth might have similar structures, gaps where the particle density drops enough to allow a spacecraft to pass through with acceptable risk. Identifying those gaps, mapping them, and timing launches to exploit them would become the defining discipline of this world's space program. Launch windows wouldn't be dictated only by orbital mechanics and planetary alignment. They would be dictated by ring geometry, the rotation of gap structures, the density fluctuations within the ring, the seasonal tilt of the ring plane relative to the launch site. Armor means building spacecraft tough enough to survive the crossing. This is possible in principle but enormously expensive in practice. Whipple shields, layered barriers of metal and ceramic designed to break up impacting particles before they reach the inner hull, are already used on the International Space Station to protect against micrometeorite impacts. Scaling that protection for a transit through a dense ring field would add significant mass to every spacecraft, driving up launch costs and reducing payload capacity. A moon mission that costs billions on our Earth might cost tens of billions on a ringed one, simply because of the additional shielding required to survive 30 minutes of ring transit. Equatorial launch sites would bear the greatest burden. Cape Canaveral, the Guyana Space Center in Kourou, the launch facilities on the equator that our civilization built specifically because equatorial launches gain a free velocity boost from the Earth's rotation. All of these would be directly beneath the densest part of the ring. Rockets launched due east from the equator, the most fuel-efficient trajectory for reaching orbit, would fly straight into the ring's thickest regions. The velocity advantage of an equatorial launch would be partially or fully offset by the cost of surviving the ring crossing. Higher latitude launch sites might become more attractive despite their inherent disadvantage in terms of Earth's rotational velocity. A launch from Baikonur in Kazakhstan at 46 degrees north or from Vandenberg in California at 35 degrees could potentially reach orbits that avoid the densest ring regions, depending on the inclination chosen. Polar orbits, the sun-synchronous orbits used by many Earth observation satellites, would be particularly challenging because a polar orbit crosses the equatorial plane twice per revolution and therefore passes through the ring twice on every 90-minute trip around the planet. The GPS constellation poses a specific dilemma. The Global Positioning System relies on a network of satellites orbiting at roughly 20,200 kilometers, an altitude that places them just above the outer edge of the ring, or possibly within its outermost tenuous regions. Deploying and maintaining those satellites would require repeated ring transits, each one carrying collision risk. The navigation system that modern civilization depends on for everything from airline routing to food delivery to military targeting might be significantly more difficult, more expensive, and less reliable on a ringed Earth. Whether an alternative system, ground-based or using satellites in safer orbits, could provide comparable accuracy is an open engineering question, but it would almost certainly be less precise and more costly. The ring would not make spaceflight impossible. Humanity is resourceful, and the history of engineering is largely a history of solving problems that seemed insurmountable until someone solved them. What the ring would do is raise the barrier, every launch more expensive, every mission more dangerous, every satellite more heavily shielded. The casual, almost routine access to orbit that 21st century civilization has begun to take for granted, launching dozens of rockets per year, deploying thousands of Starlink satellites, sending tourists to the edge of space, would be far harder to achieve on a planet where a wall of high-velocity rock sits between the surface and the cosmos. The dream of leaving Earth would still exist. The engineers and dreamers and visionaries who looked up at the rings and wondered what lay beyond them would still build rockets and plan missions and push the boundaries of what's possible. The difference is that their greatest obstacle would not be gravity or funding or political will. It would be the rings themselves, beautiful from below, lethal from within, and standing between humanity and everything else in the universe. The rings would challenge our technology and limit our reach into space. They would also, over geological time, begin to challenge themselves, because no ring lasts forever, and the same particles that block our path to the stars are slowly, steadily falling back to Earth. Nothing in orbit stays there forever. Every satellite ever launched will eventually come down, dragged by the faint whisper of atmospheric molecules that reach even into the vacuum of low Earth orbit, or perturbed by gravitational irregularities in the planet below, or nudged by the pressure of sunlight itself, photon by photon, until the orbit decays and the atmosphere claims what gravity has been patiently waiting for. The International Space Station, without periodic boosts from visiting spacecraft, would fall back to Earth within a few years. Even satellites at much higher altitudes drift, decay and die on timescales measured in centuries or millennia rather than years, but the endpoint is the same for all of them. The ring is no different. It is larger, older, and vastly more complex than anything humanity has put into orbit, but the same physics applies. Ring particles lose energy through collisions with one another, through interactions with Earth's magnetic field, through the subtle drag of the extremely thin exosphere that extends far above the conventional boundary of the atmosphere, and through the gentle but relentless pressure of sunlight pushing on their surfaces. Each of these effects is tiny on any given day. Accumulated over millions of years, they are transformative. The innermost ring particles are the first to go. Closest to the planet, they experience the strongest atmospheric drag, vanishingly faint at 9,000 kilometers, but not zero. Their orbits shrink imperceptibly, spiraling inward over millennia until they dip low enough to encounter meaningful atmospheric resistance. At that point, the process accelerates. Drag increases as the particle descends into denser air, which lowers the orbit further, which increases the drag further still. The final phase is fast. A particle that spent 10 million years slowly spiraling inward might cross the last 500 kilometers of its descent in a matter of weeks, heating up as it plows through thickening atmosphere, glowing first dull red, then orange, then white, before either burning to ash or, if it's large enough and dense enough, punching through the atmosphere and striking the surface. On Saturn, Cassini measured this process directly. Ring particles fall into Saturn's atmosphere at a rate of roughly 10,000 kilograms per second, enough to fill an Olympic swimming pool every half hour, pouring off the inner edge of the rings in a steady, invisible rain. The material spirals along Saturn's magnetic field lines, entering the atmosphere at high latitudes and chemically altering the upper layers as it falls. The water from Saturn's icy ring particles actually changes the composition of the stratosphere in the zones where ring rain is concentrated. Earth's ring would undergo the same process, though the details would differ. Rocky particles entering Earth's atmosphere wouldn't deliver water. They'd deliver silicates, iron, nickel, carbon, the elemental palette of asteroidal rock. The smallest particles, grains of dust and sand, would burn up entirely in the upper atmosphere, adding their mass to the thin layer of meteoric smoke that already exists at altitudes between 70 and 100 kilometers. This smoke, a persistent haze of nanometer-scale particles from the roughly 40 tons of cosmic dust that already enters Earth's atmosphere every day, would thicken. More metallic aerosols in the mesosphere would mean more nucleation sites for ice crystals at high altitude, potentially increasing the frequency and brightness of noctilucent clouds. those eerie electric blue formations visible at high latitudes during summer twilight. The larger particles would put on a show. A ring steadily shedding material would produce meteor activity far above the background rate we experience today. Not the occasional shooting star that catches your eye on a clear night, but a persistent nightly drizzle of streaks, dozens per hour visible to the naked eye, hundreds per hour detectable by radar. A ceaseless rain of light as the ring feeds the atmosphere with its slowly grinding debris. Major annual meteor showers like the Perseids or the Geminids, which on our Earth produce at most 100 or so visible meteors per hour at their peak, would be unremarkable on a ringed planet. The ring would make every night a meteor shower, and occasionally something larger would come down. Ring particles are not uniformly small. Collisions within the ring produce fragments across a wide range of sizes, from microscopic dust to boulders several meters across. The smallest are the most numerous and the most benign. The largest are rare but consequential. A meter-wide chunk of rock entering the atmosphere at orbital velocity, 6 to 8 kilometers per second, would produce a fireball brighter than the full moon, visible across a 1,000-kilometer radius, and deposit a shockwave audible on the ground below. Most of its mass would ablate during descent, but a fragment the size of a fist or a football could survive to reach the surface. Over the lifetime of a civilization, these events would be common enough to be familiar, rare enough to be frightening, and unpredictable enough to be impossible to fully prepare for. Larger impacts, ring fragments 10 meters across or more, would be genuinely destructive. An object of that size, striking the atmosphere at 6 kilometers per second, would explode in the lower atmosphere with an energy release comparable to a small nuclear weapon. The Chelyabinsk event of 2013, caused by a roughly 20-meter asteroid entering over Russia, shattered windows across a wide area, injured more than 1,000 people, and delivered a shockwave that circled the globe twice. Events like Chelyabinsk are currently estimated to occur once every 50 to 100 years. On a ringed Earth, with a vastly larger reservoir of debris continuously feeding material into decaying orbits, the frequency could be significantly higher, perhaps once a decade, perhaps more, depending on the ring's mass and particle size distribution. Cities beneath the ring's orbital track, those within the equatorial and low latitude belt, would face the highest statistical risk, simply because ring material descends preferentially toward the equator. The same latitudes that bear the ring shadow's climatic burden would also bear the brunt of its falling debris. The tropics, already dealing with reduced sunlight and disrupted monsoons, would additionally contend with a persistent rain of space rock that their higher latitude neighbors largely avoid. The psychological dimension is worth considering. In our world, asteroid impacts are abstract threats, statistically real but experientially invisible to almost everyone alive. Most people go their entire lives without seeing a fireball, without hearing a bolide explode overhead, without any visceral reminder that objects from space occasionally reach the ground. On a ringed Earth, the reminder would be nightly. The meteors would be constant, the fireballs would be periodic, and the rare, violent impacts, the ones that shatter windows and leave craters, would be frequent enough that every generation would have a story. Every culture would have a name for the phenomenon. Every child would grow up knowing that the beautiful arch overhead occasionally drops pieces of itself on the world below. The ring would thin over time. This is inevitable. Every particle that falls is a particle the ring loses, and no mechanism replenishes the supply. The ring's total mass decreases with each passing millennium, the brightest bands slowly dimming, the densest regions gradually becoming translucent. On Saturn, the rate of loss suggests the current rings have perhaps 100 million years remaining. An Earth ring of comparable density might last a similar duration or longer if its rocky composition makes it more resistant to certain decay mechanisms, or shorter if Earth's stronger magnetic field and closer proximity to the Sun accelerate the loss. Over tens of millions of years, the ring would visibly evolve. Gaps would widen as resonance effects cleared certain orbital zones. The overall brightness would decrease as the total mass of reflecting particles diminished. The arch that once blazed across the night sky would soften, fade, become a ghostly remnant of its former self before finally dissolving into a thin haze of scattered particles, too sparse to see with the naked eye. And then it would be gone. The sky would darken. The Milky Way would reappear, faint at first, then vivid, as the last traces of ringshine faded, and true night returned to a planet that hadn't experienced it in geological ages. Humanity, if it still existed in recognizable form, would look up at a sky its ancestors had never seen and wouldn't recognize. The arch that had defined their mythology, guided their navigation, shadowed their climate, and blocked their path to the stars would be nothing but a memory, preserved in temple carvings and ancient texts and the ring-shaped motifs woven through every artistic tradition on the planet. The rings would leave scars, craters in the equatorial belt, meteoritic dust woven into geological strata, climatic patterns still adjusting to the sudden return of unfiltered sunlight across the tropics, and a species shaped by millions of years of living beneath a permanent arch of light, suddenly confronting a sky that, for the first time in living memory, goes completely dark at night. The rings would have changed everything about the planet and the people on it. Not just the climate, not just the sky. The way humans think, what they believe, how they organize their civilizations, what they consider beautiful and what they consider possible. All of it shaped by the presence of something that was always there, always visible, and always slowly falling apart. Consider two children born on the same day, on the same continent, under the same sun. One grows up on our Earth, open sky, dark nights, a round moon drifting through the constellations. The other grows up on the ringed Earth we've been building across these chapters, the arch overhead, the silver glow at midnight, the shadow that sweeps across the tropics with the turning of the year. By the time those children are old enough to wonder about the world, they are already different people. Not because their biology is different, not because their brains are wired differently, but because the world that shaped their assumptions, their instincts, and their sense of what is normal has been fundamentally altered by a band of rock orbiting 40,000 kilometers overhead. The child on the ringed Earth has never experienced true darkness. Her earliest memories include the glow, that soft, persistent illumination that fills the bedroom even with the curtains drawn, that lights the path between the house and the barn, that makes the night a dimmer version of the day rather than its opposite. She doesn't fear the dark the way children on our Earth sometimes do, because darkness, for her, is an abstraction. Something described in old stories, referenced in poetry, but never actually encountered. The idea that the sky could be black, genuinely, completely black, with nothing but pinpoints of light scattered across it, would strike her as exotic, almost frightening, the way a child raised in the tropics might react to a description of a blizzard. Her sense of direction is different too. She knows, without thinking about it, which way is south, because the arch is there, always there, and south is the direction it climbs toward. She navigates by ring the way we navigate by sun, automatically, unconsciously, the orientation baked into her spatial awareness by years of glancing up and noting where the bright band sits. She has never been lost in the way that a person on our Earth can be lost, disoriented, directionless, stripped of all reference points. The ring won't allow it. Wherever she goes, the sky tells her where she is. Her calendar is shaped by the ring shadow. She knows the equinox not as an astronomical abstraction defined by the tilt of an axis she's never seen, but as the weeks when the shadow passes over her latitude, when the air cools and the light dims and the garden produces less and the elders say the ring is crossing. She marks time by shadow and light the way our ancestors marked it by solstice and moon phase, not because she's been taught to, but because the rhythm is woven into the fabric of her daily life in a way that makes any other system feel arbitrary. Now scale that childhood across a civilization, across thousands of years of civilization. Agriculture on the ringed Earth would have developed differently from the start. The first farmers 10 or 12,000 years ago would have had to contend not only with the usual variables, soil quality, rainfall, temperature, day length, but also with the ring shadow's seasonal transit. Fields in the shadow zone would produce less during the weeks of reduced sunlight, and the pattern of that reduction would vary by latitude in ways that demanded local knowledge and careful observation. Farming communities at 15 degrees north would experience the shadow at a different time and intensity than communities at 30 degrees, and the crop varieties, planting schedules, and harvest rituals that developed in each region would reflect those differences. A global agricultural tradition calibrated to ring shadow rather than solstice, or more precisely, to the interaction between both, would produce a patchwork of regional practices far more diverse than what we see on our own Earth, where the primary variable is latitude and season alone. Population distribution would reflect the shadow's geography. The equatorial band, despite its fertile soils and abundant water, would be the most shadow-affected zone during the equinoxes, creating a tension between the region's natural productivity and its periodic light deficit. Some civilizations might thrive there regardless, adapting their agriculture to the rhythm of the shadow the way Nile cultures adapted to the rhythm of the flood. Others might preferentially settle at latitudes where the shadow is less intense, the mid-latitudes between 25 and 45 degrees, where the ring shadow passes more briefly and the growing season, while shorter than in the tropics, is more predictable. The great population centers of this alternate Earth might cluster not along river valleys and coastlines alone, but along the latitudes where shadow and sunlight are most favorably balanced. Trade would follow the shadow. Regions experiencing peak shadow, and therefore reduced agricultural output, would import food from regions in full sunlight. The seasonal migration of the shadow would create a rolling wave of demand that moved across latitudes through the year, driving trade routes and economic relationships that have no parallel on our Earth. A merchant class specialized in shadow arbitrage, buying grain cheap in sunlit regions and selling it dear in shadowed ones, could emerge as one of the defining economic forces of this world, as influential as the spice traders or Silk Road merchants of our own history. The military implications are less comfortable to consider but impossible to ignore. Civilizations in permanent competition for resources would notice that the ring shadow weakens their rivals at predictable times. An empire at 30 degrees north, knowing that its equatorial neighbor enters the shadow zone every March and September, might time its campaigns to coincide with those periods of agricultural stress and reduced morale. Shadow warfare, the strategic exploitation of ring-induced vulnerability, could become a recognized doctrine, as much a part of military planning as terrain, weather, and supply lines are in our world. Art on the ringed Earth would be saturated with the arch. Every visual tradition, painting, sculpture, mosaic, textile, architecture, would reference the rings the way our art references the horizon, the sun, and the human figure. The arch motif would be foundational, appearing in everything from the curved lintels of doorways to the sweeping lines of bridges to the decorative borders of manuscripts. Abstract art might explore the ring's geometry, its curvature, its thinness, the play of light and shadow across its surface. Representational art would depict it in every landscape, every cityscape, every portrait where the sky is visible. An art historian from our Earth looking at the collected visual culture of this ringed world would be struck by the ubiquity of the curve, a single, sweeping arc repeated across every medium, every era, every culture, as inescapable in their imagery as the ring itself is inescapable in their sky. Music would carry the ring in different ways. Songs about constancy, about permanence, about things that endure while everything else changes. These themes already exist in our music, but on a ringed Earth they would find their ultimate symbol in the arch that never sets. Lullabies would reference the ring's glow as a source of comfort. Work songs timed to agricultural rhythms would mark the shadow's coming and going. Sacred music performed during equinox ceremonies, when the ring flares brightest as the sun aligns with its plane, would carry a specific emotional register tied to that visual spectacle, a combination of awe and solemnity and anticipation that has no exact equivalent in our musical tradition. And the question that would define philosophy on this world, the question that every thinking person would eventually ask, is not, why are we here, but why is the ring here? The ring is visible, physical, undeniable. It demands explanation in a way that the empty sky does not. An empty sky invites wonder but permits indifference. A ringed sky insists on engagement. You cannot look up and ignore it. You cannot build a worldview that doesn't account for it. The ring forces the question, and the question, pursued across generations, across cultures, across the slow accumulation of knowledge from mythology to philosophy to science, would be one of the great engines of intellectual progress on this world. From the outside, from a spacecraft approaching this alternate Earth, the planet would be stunning. A blue marble wrapped in a thin, luminous band, the ring catching sunlight and scattering it into a pale halo around the planet's equator. Our Earth is beautiful from space, but a ringed Earth would be breathtaking in a way that stops conversation. It would look intentional, designed, as though someone had placed a jeweler's setting around a gemstone and stepped back to admire the result. From the inside, the experience would be more complicated. The beauty would be real, but so would the shadows, the falling debris, the blocked stars, the limited access to space, the climate distortions, and the constant, quiet awareness that the most prominent feature of your sky is slowly, grain by grain, falling apart. As our journey through this ringed world comes to an end, we're left with a question that cuts deeper than science or speculation. A question about the world we actually live in, the sky we actually have, and what it means that our planet chose a moon over a ring. Earth doesn't have rings, it has a moon. That simple fact, so obvious it barely seems worth stating, is the result of a choice that was never made. 4.5 billion years ago, when Theia slammed into the young Earth and blasted a disk of molten debris into orbit, the physics could have gone either way. If the debris had been less massive or more widely dispersed, or if the collision had happened at a slightly different angle, the material might have spread into a stable ring rather than clumping into a single body. The disk might have settled, cooled, and persisted, a permanent band of rock and dust orbiting above the equator for billions of years, slowly raining down, casting shadows, glowing at night, shaping every civilization that ever arose beneath it. Instead, gravity gathered the debris together. Particles collided, merged, grew. Within a few thousand years, perhaps less, the ring was gone, and in its place hung a sphere of rock 800 kilometers wider than the distance from Madrid to Moscow. The Moon. It was not a gentle birth. The early Moon orbited far closer to Earth than it does today, perhaps only 20 or 30,000 kilometers above the surface. Close enough that it would have filled a significant portion of the sky, close enough that the tidal forces between the two bodies were enormous, flexing the Earth's still molten crust and generating heat that kept both worlds partially liquid for millions of years. The Moon has been receding ever since, drifting outward at 3.8 centimeters per year, trading proximity for stability, slowly settling into the quiet, distant orbit we know today. What it left behind is a planet that works. The Moon stabilizes Earth's axial tilt. Without it, the gravitational influence of Jupiter and the Sun would tug on Earth's rotational axis, causing it to wander chaotically over millions of years, swinging from nearly 0 degrees, which would eliminate seasons entirely, to more than 40 degrees, which would produce seasons so extreme that the poles would bake in summer sunlight while the equator froze in winter darkness. Mars, which has no large moon, experiences exactly this kind of axial chaos. Its tilt has varied between 15 and 35 degrees over the past few million years alone, and may have swung even more wildly in the distant past. Earth's tilt, by contrast, has stayed between 22 and 24.5 degrees for hundreds of millions of years. The Moon holds it there, acting as a gravitational anchor that dampens the oscillations and keeps the axis pointed in roughly the same direction, century after century, millennium after millennium. Stable tilt means stable seasons. Stable seasons mean predictable climate. Predictable climate means ecosystems can specialize. Species can adapt to reliable cycles of warmth and cold, wet and dry, and biological complexity can accumulate over hundreds of millions of years without being periodically scrambled by wild swings in axial orientation. The extraordinary biodiversity of our planet, the product of billions of years of evolution operating under broadly stable conditions, owes a quiet, largely unrecognized debt to the Moon. The Moon also drives the tides. Twice each day, the gravitational pull of the Moon raises the oceans by a meter or more along most coastlines, creating the rhythmic advance and retreat of water that defines the intertidal zone, one of the most biologically productive habitats on the planet. Tidal pools, salt marshes, mangrove forests, estuarine mudflats, all of these ecosystems depend on the daily pulse of the tides to deliver nutrients, flush waste, and maintain the delicate boundary between marine and terrestrial life. Some biologists have speculated that the intertidal zone may have played a crucial role in the transition from sea to land, providing a gradient of conditions, wet to dry, salt to fresh, submerged to exposed, that allowed organisms to adapt incrementally rather than making a single, impossible leap. A ring would do none of this. Rings don't stabilize axial tilt. They lack the concentrated mass needed to act as a gravitational anchor. Rings don't drive meaningful tides. Their total mass is a tiny fraction of the Moon's, and tidal force depends on mass and proximity in ways that a diffuse band of particles cannot replicate. A ringed Earth without a Moon would be a planet with chaotic seasons, minimal tides, reduced intertidal habitat, and a climate system vulnerable to the kind of axial wandering that would periodically render large portions of the surface uninhabitable. The trade-off, in other words, is not just aesthetic. It's existential. The Moon made Earth livable in ways that a ring never could. The ring would have been more beautiful, more visually dramatic, more culturally prominent, more immediately striking to anyone who looked up. The Moon is subtle by comparison. A pale disk that waxes and wanes, sometimes hidden by clouds, sometimes outshone by city lights, easy to take for granted, easy to forget. You can live your entire life in a modern city and barely notice the Moon. You could not live a single day on a ringed Earth without noticing the rings. And yet, the Moon steadies the axis. The Moon drives the tides. The Moon lit the night just enough for our ancestors to see predators approaching, to travel after dark, to plant and harvest by its phases. The Moon provided the first natural clock, a 29.5-day cycle of waxing and waning that gave early humans a way to track time longer than a day and shorter than a year, a rhythm that shaped the earliest calendars and may have influenced the development of counting and mathematics itself. Rings would have given us beauty. The Moon gave us stability. That distinction carries a certain philosophical weight, particularly when you consider that Saturn's rings, the most beautiful ring system we know of, are dying. 10,000 kilograms per second, spiraling into Saturn's atmosphere, slowly draining the most photogenic feature in the solar system. In 100 million years, Saturn will be a bare, banded gas giant, indistinguishable from the planet it was before its rings formed. The rings are an event, not a permanent feature. A spectacle with a beginning and an end. We happen to exist during the middle act. Earth's Ordovician ring, if it existed, was the same kind of event. It came, it stayed for 20 to 40 million years, it cast its shadow, it rained its debris, it may have helped trigger one of the worst mass extinctions in the planet's history, and then it faded. The planet recovered. life diversified. The Silurian forests grew. Fish learned to breathe air. Amphibians crawled onto land. Reptiles, mammals, birds, flowers, all of them arose on a planet that had once worn a ring and survived its loss. There is something reassuring in that resilience, and something humbling in the realization that the feature we spent this entire documentary imagining, a permanent, beautiful, terrifying ring around our world, has already come and gone. Earth wore its ring, Earth shed its ring, and we are the descendants of everything that survived. The universe is full of rings. Every giant planet in our solar system has them. Saturn's are the most famous, Jupiter's the faintest, Uranus's the darkest, Neptune's the most fragmented. Astronomers have detected ring structures around exoplanets orbiting distant stars, and there is no reason to think rings are rare in the galaxy. They may be as common as moons, as common as atmospheres, as common as oceans. Somewhere out there, around a star we haven't studied yet, a rocky world with liquid water and a thick atmosphere might orbit with a ring of debris above its equator. A planet where the arch glows every night, where the shadow crosses the tropics twice a year, where the creatures that evolved beneath it have never known a sky without it. We will probably never visit that world. We may never even detect its ring from the distance of 100 light years. What we can do is imagine it, and in imagining it, understand something about our own planet that we might otherwise take for granted. Our sky is dark at night, truly dark, dark enough to see the Milky Way from a mountaintop, dark enough to count the stars, dark enough to feel small and alone and awed by the sheer depth of the universe stretching away in every direction. That darkness is not a deficit, it is a window. Every photon that reaches your eye from a distant galaxy traveled millions or billions of years to get there, and it could only reach you because nothing stood in the way. No ring, no glow, no veil of reflected sunlight, just the clean, cold vacuum of space, and the ancient light that has been crossing it since before the Earth existed. The moon hangs in that darkness, quiet and familiar. It doesn't blaze across the sky in a great arch. It doesn't cast climate-altering shadows or block the path to the stars. It doesn't rain debris onto the tropics or drown out the constellations with its glow. It just orbits, steady and slow, pulling the tides, holding the axis, reflecting just enough sunlight to turn a dark night into something navigable and beautiful without overwhelming it. If you step outside tonight and look up, you won't see rings. You'll see the sky your ancestors saw, the same moon, the same stars, the same darkness that inspired 10,000 years of mythology and 500 years of science and the first tentative steps off this planet and into the void beyond. That sky is quieter than the ringed sky we imagined together, emptier in some ways, less dramatic. It is also the sky that made us possible, the stable seasons, the predictable tides, the dark nights that showed us the universe and made us want to reach it. Every rover on Mars, every telescope in orbit, every footprint on the lunar surface exists because our sky was clear enough to see through and open enough to fly through. We got the moon instead of the rings. And the moon, for all its quiet modesty, may have been the better deal. The Ordovician ring came and went. Saturn's rings are fading. Our moon is drifting slowly outward, a few centimeters farther each year, and will continue drifting for billions of years to come. Nothing in the solar system is permanent. The rings were always temporary. The moon is temporary too, on a long enough timescale. Even the sun will eventually exhaust its fuel and swell into a red giant that swallows Mercury and Venus and scorches the Earth beyond recognition. Everything ends. What matters is what happens in the time between the beginning and the end. And in that time, in this particular window of cosmic history, we have a moon that steadies the world, a sky that reveals the universe, and a planet that, 4.5 billion years ago, turned a ring into a companion. Rest now, under that sky, the one without the arch, without the glow, without the shadow sweeping across the latitudes, the quiet sky, the dark sky. the sky that let you see the stars and wonder what they were, and then build the instruments to find out. The moon is up there somewhere tonight. It might be full, or it might be a thin crescent, or it might be hidden below the horizon, waiting to rise. It doesn't matter. It's there. It has always been there. Born from a ring, forged from a collision, drifting outward ever since, holding the Earth steady while the centuries pass, and the species come and go, and the tides rise and fall in the rhythm they've kept for 4 billion years. Your moon was once a ring around this planet, and the fact that it became something else, something quieter, something stabler, something that made this world possible, might be the luckiest thing that ever happened in the history of the solar system. Sleep well on a planet that chose a moon.